So good evening all. Means we'll start in few minutes. People are still joining. So let some more people join, and still we have 2 minutes to 6.
Okay. Yes, here Manirul is here.
I
I'm
can see you, Manu.
okay. So, hi, Anirbanda. Okay, just let me switch on the.
More people are joining. So we'll start in
Okay.
people are still joining. So let some more people join. And so this is echo from YouTube. Let me 2 minutes to 6.
Okay. Yes, here Manirul is here.
Ah,
Okay, maybe.
Sandeep, can you hear me?
Yes, I can hear you, sir.
So there is some small issue. Means I don't see the share button now.
Share button?
Oh. I can see the share button from my side.
Okay, so if you cannot share, then we'll check. That means just can you try?
Okay.
Means before we start, just try to share. That means if it is working or this I
Okay, and let me I'm sending the share.
okay. Now it's
uh,
coming to me. Allow. So I allow.
Okay. So I'm trying to share my screen. Yeah, okay.
So now it came to my window also. So okay. So
Yes,
no. So it's
okay.
time. It means 1 minute past 6, and yesterday we faced some time issue. So without further delay, we would like to start. And in the beginning itself, I would like to request all the speakers to take only 15 minutes per talk, and then so that we can have 5 minutes per discussion. And I also request uh, all the session chair to strictly maintain the time. And I would like to request now my colleague Dr. Sandeep Misra to introduce the session chair, and then from there session chair will take over the first session of the second day. So over to Sandeep.
So, welcome all to the session one of the day two, and Dr. Guru Prasad Kadam will be chairing this session. So, he is a faculty in JIIT, and before that, he has done his PhD from PRL. And right now, he is basically working on the foundational aspects of the quantum mechanics. So, let Guru take over. Guru, you are here.
Yeah, Sandeep.
Yeah.
Can
You
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 hear
can
me?
take over.
Can you hear me?
Yes,
Yeah,
you are
I can
audible.
hear you.
You are
Okay.
audible, so you can
Thank
conduct
you,
the session.
Sandeep. Thank you, Sandeep. Welcome all to this session on quantum information. Our first speaker is Dr. Manirul Ali from Chennai Institute of Technology. He'll be talking about near perfect noisy quantum state teleportation. So, Dr. Manirul, over to you. You may commence your talk. You have already shared the slides.
Thank you. Thank you. I first thank the chair, and I should thank Professor Sandeep Mishra and Professor Anirban Pathak for giving me this opportunity to present our work here in this meeting. So this is our work. This is a recent work we have done, near perfect noisy quantum state teleportation, and this paper is now on archive also. So I am from Chennai Institute of Technology, and as we all know that achieving high fidelity of quantum teleportation, fidelity means the teleportation is not always perfect. So there is some imperfect teleportation. So then we call about the fidelity of the teleportation. So what exactly that quantity relevant to our work, I will explain to you. So achieving high fidelity of quantum teleportation in a noisy environment, that means in presence of noise, is an essential requirement for its real world applications such as quantum repeaters, which is known as the main building block of quantum network through which quantum information processing can be done remotely. So quantum teleportation plays a very important role in various tasks like long distance quantum communication, distributed quantum computation, etc. And actually, our work was motivated from a paper published in 2024 in Science Advanced Journal. This is the paper, Overcoming Noise in Quantum Teleportation with Multipartite Hybrid Entanglement. And in this work, actually, I briefly outline the result. So in this work, a a variant of the standard quantum teleportation protocol is considered based on a hybrid entangled state shared between the photonic qubits SA. Here, if I am slightly moving my mouse, SA and SB. SA belongs to Alice, SB belongs to Bob. So this there is an entangled state shared between these photonic qubits, so SA and SB with Alice and Bob. And so this the hybrid entangled state is prepared by coupling the photonic polarization states of the two photons with continuous frequency modes having a joint frequency distribution. Then Alice subjects her auxiliary qubit SA of the shared entangled pair to a controlled dephasing medium, controlled dephasing interaction by passing it through a suitably chosen birefringent medium, while the input qubit, that is the state to be teleported, ST, that is assumed to be remain isolated from the environment. And subsequently, in the next step, Alice performs a Bell state measurement as usual between jointly on ST and SA on her possession, and communicates the measurement outcome to Bob, based on which Bob applies the appropriate unitary transformation on his qubit. And as a result of this measurement, the hybrid entanglement shared between Alice and Bob is converted into the system environment, a system environment entanglement correlation, or system environment entanglement associated with Bob's qubit. So here, the Bob's qubit is effectively so let me repeat again. As a result of this measurement, Bell state measurement, the hybrid entanglement shared between Alice and Bob is converted into system environment entanglement associated with Bob's qubit here. And finally, Bob subjects his qubit to a controlled dephasing interaction by passing it through a suitably chosen birefringent medium. So Bob then again apply an extra noise, dephasing noise, to decouple his qubit from the environment, and resulting to a high fidelity teleported state at Bob's end. So this was the proposal. So here in our work, in this work, we provide a new protocol for this for the noisy quantum teleportation. That means teleportation in presence of noise, and in contrast to the above science advance work, our proposed protocol has the following distinct features. First, that our protocol does not require any initial preparation of hybrid. We don't need hybrid entanglement like this for polarization between polarization and frequency states, frequency modes. And Bob has to do nothing for the noise cancellation. Like unlike the one I described, where Bob has to apply another dephasing noise on his qubit after the Bell state measurement. So that is a distinct feature. Another feature is that unlike that science advance scheme, our scheme is not restricted to photonic qubits only. So our scheme is applicable to a general two-level system, and a key advantage in our protocol is that Bob does not require any pre-shared information about the noise at Alice's end. And also in our scheme, we managed to avoid the decoherence effects completely from Alice's side. So because actually we exploit the existence of a decoherence-free subspace at Alice's wing. And in our teleportation protocol, there is another difference is that in our teleportation protocol, Alice needs to communicate only 1.5 bits of classical information, unlike the standard case where 2 bits of classical information is required. So these are the key features of our protocol. And so here I'm going into the details of this noisy teleportation protocol. As we know that Alice want to send the quantum information about a qubit A1 to Bob. So A1 and Alice and Bob share an entangled state A to B, between A2 and B. And so A1 is the unknown quantum state which Alice wants to send to Bob. So then, this is the initial unknown state I have written here, psi in, which is alpha up plus beta down, which is in access. Alice access this particle, and the entangled state shared between Alice and Bob is this one. So we have considered not necessarily a maximally entangled state. Here it is a non-maximally entangled, pure entangled state where mu and lambda can be anything. If it is 1/√2, then it is maximally entangled. And the joint, then we can write down the joint 3-qubit state of Alice and Bob. That means for these three particle A1, for these three particle A1, A2 and B, in this way. And then we have what is in the protocol, that this particle A1 and A2, they evolves under a common noisy environment. We take the here as a common dephasing noise, and the particle B evolves under a local. So particle B is at a distance at Bob's position. So B evolves under a local dephasing noisy environment. And so this is the time evolution. I briefly describe the time evolution in Alice's wing. So Alice has these two particles, A1 and A2. They evolve under the common environment, common dephasing environment. So this is the interaction. So these are the two particles, two spin-half particles. This is the environment, and this is the system environment interaction. So these two spins are collectively, this capital SZ is the collective spin operator of these two spins, and we can derive the master equation, quantum master equation for this system reservoir model, where the state for these two qubit can be determined at any given time. So this is the Hamiltonian part. This is the dissipative term in the master equation, and the dissipative terms is explicitly written over here. And in this dissipative term, we see that there are coefficients like time dependent functions at and alpha t, which are basically determined by the reservoir property, that is this reservoir or the environment's spectral density. We call it spectral density j omega.
Munirul, you have 5 minutes.
Okay. So I have to go fast actually. So and at Bob's side, this the qubit at Bob's side evolves under a local environment which is described over here. So that is also described by some master equation, and we can actually have the time evolution from there. So what happens after that noisy interaction? So after that noisy interaction, this noisy time evolutions from, say for example, t equal to 0 to t equal to tau in both the wings of Alice and Bob. Alice performs a Bell state measurement at a particular time t equal to tau jointly on her qubits A1 and A2, and consequently the resulting 3-qubit joint state A1 A2B becomes this. So if one can follow the steps, then one can have this joint state. So here I have written in a nice way that we can see that this left hand side we have these 4 Bell state, phi plus, phi minus, psi plus and psi minus, which are written in the bottom. And on the right hand side, the reduced state of the Bob's qubit is written over there. So if we can minutely follow that, then we can see that for the and this is basically the state I have written over here, that in this way, because I want to show that the effects of the noisy channel and the information about this non-maximally entangled state, all these informations are transferred to Bob's side. So all the noisy effects we can have after that operation comes to Bob's qubit actually. This A tau, B tau are this small A tau, B tau, they are the decoherence factors as a result of that environmental interaction. And here I just want to point out that when Alice obtained this state phi plus, that Bell state, because she is doing the Bell state measurement, when she obtained phi plus, Bob state is will collapse to this rho phi plus, and when Alice obtained phi minus, his state Bob state will be reduced state will be rho phi minus. And when Alice obtained psi plus, Bob state is rho psi plus, here as a function of b tau only. And when she obtains psi minus, Bob state becomes rho psi minus b tau. So here what I want to point out here that when Alice obtained this phi plus and phi minus, this decoherence factor, both the decoherence of Alice and Bob side take the role. I mean, they play all the cumulative effect of noise from Alice's side and Bob's side, they add up. But when Alice obtains psi plus or psi minus, the Bob side state, that is completely, I mean, independent of any noise from Alice's side. We don't see here the decoherence factor A tau for this outcome psi plus and psi minus, because here what we are actually doing, we are exploiting a decoherence free subspace of a common dephasing in Alice's wing. So because these two particles evolves under a common dephasing in Alice's wing, there we have a decoherence free subspace. So here I explicitly have written those reduced density matrices of Bob's qubit on the right. Yeah, so rho phi plus, rho phi minus, rho psi plus and rho psi minus, they are the reduced density matrix at Bob's wing when Alice actually obtained those outcomes, phi plus, phi minus, psi plus and psi minus. So it is very clear from here that for those outcomes, phi plus and phi minus, the decoherence is much more because of the cumulative or because this decoherence effect actually add up because of these two decoherence factor A tau and B tau. But here in case of psi plus and psi minus, we can completely avoid any decoherence from Alice's wing. So that's why here we don't see the factor A tau here for these two outcomes, the bottom two outcomes. Okay, the expression for A tau and B tau is written over here. And so, okay, let me go ahead. So I don't have much time about to describe about the decoherence free subspace, but just I want to point out that so the states which are like up down or down up or their superposition, they belongs to a subspace where this decoherence, the common dephasing does not affect them. So this blue density matrix element, they don't get affected by this decoherence. So exactly the psi plus and psi minus, those are the states which belong to this decoherence free subspace. So through them, the noise cannot propagate to Bob's wing. So that is the strategy here. So that's why for these two outcomes, we don't have the noise effect of noise from Alice's side. And we calculated actually, so we have this output state for these two outcomes, and for that we can obtain the teleportation fidelity. And because the target state was this, and the fidelity of teleported state.
Dr. Manirul, would you please try to conclude? We are running out of time.
Okay. Okay, so let me conclude. So the average teleportation fidelity here I showed the average we have calculated is this one. So here from this expression we can see that this average fidelity only depends on this B tau. That means the decoherence factor in the Bob's wing. And okay, so this decoherence factor is written explicitly, the expression over here. And okay, in contrast, if we consider that phi plus and phi minus, the teleportation fidelity will be very bad actually to the power. So for the psi plus and psi minus, we can see the teleportation fidelity is something like this. The decay factor is e to the power minus 2 gamma over here. Then log some factor is also there. But for phi plus and phi minus, the teleportation fidelity is something like e to the power minus 10 gamma. So the decay factor, you can see that's very severe effects happening because of the combined decoherence effect from Alice's and Bob's side. So side by side, we can compare this fidelity and that fidelity, and with the different noise parameters, actually we showed how this fidelity actually depends, and in the long time they go close to this classical teleportation fidelity. So and one very important point I just will mention, and then I'll complete that the time. Here we plot with time, right? The teleportation fidelity. The time is very important factor here. That is the when the up to which actually you are allowing the evolution of the qubits under the noise, and when Alice is making the measurement. So that time, depending on the time, actually the fidelity will be different. And here some estimate with different values of the concurrence of the shared entangled state, how the fidelity varies for different noise parameters, of course. And we have also considered a mixed state, not only just pure entangled channel for the teleportation. For mixed state also, we have similar results, which I don't have much time to explain, but yeah, here I should conclude. And yeah, if there is any question, please. Yeah.
Yeah, we may take one or two questions. Okay, if there are no questions, thank you, Manirul, for a very nice talk. You may now unshare your screen.
Okay, thank you so much. I just
There is a question in the chat box.
Okay, so we have a question in the chat box. Manirul?
okay, just let me see the chat box. Okay. Uh, experimental work. No, it is not an experimental work, but we have given a experimental proposal at the end of the paper. If you can please go through that archive paper where we have a proposal for with photonic qubits under dephasing noise. And Alice and Bob, how much you have taken the distance? So the distance factor we have not considered in this model, so that that we have to think how to incorporate in the model. But here only the noisy environment and the system in the environment interaction standard spin boson model actually we have considered. Yeah. So I have given my email. You can contact if you need some more
Yeah.
details.
Okay. So now let's move on to our next speaker. Our next speaker is Christopher Verbos from QAGI LLC. Christopher, are you there?
Yes, we're here.
Yeah. Okay. So can you share your screen?
Yes, I've just hit the
Yeah.
share button. Does it show up?
Yeah. Okay. So
Okay.
Christopher will be talking about the thermal quantum optimization, a new paradigm for quantum computing. So over to you, Christopher. You may start your talk.
Hello, everyone. Today I'll present the paper Thermal Quantum Quadratic Optimization Harnessing Reservoir Coupling for Combinatorial Optimization. The central idea of the paper is unusual but very interesting. Instead of trying to eliminate thermal interaction with the environment, we propose using that thermal coupling as a computational resource. The system begins in a more exploratory quantum regime and then, through controlled coupling to a thermal bath, transitions towards the ground state of the optimization Hamiltonian. So the main claim is that thermal relaxation can help solve the Ising type combinatorial optimization problems rather than only harming quantum computation. Most quantum optimization approaches treat the environment as the enemy. In gate-based quantum algorithms like QAOA, decoherence is something to beat by finishing the circuit before the state is corrupted. In adiabatic quantum annealing, thermal excitations are also seen as undesirable because they can knock the system out of the ground state. TQQO starts from a different premise. It asks, what if quantum superposition is useful for exploring the search space, but thermal relaxation is useful for actually settling into low-energy solutions? In other words, can we combine the exploratory advantage of quantum dynamics with the convergent behavior of Boltzmann thermalization? That is essentially the core conceptual shift in this paper. Instead of fighting the reservoir, TQQO tries to exploit it. The optimization problems are written as Ising Hamiltonians. Each qubit has a local field term, shown by the H sigma z part, and pairwise interaction terms shown by the J sigma sigma part. This is a standard encoding used for many combinatorial optimization problems, including max-cut and other NP-hard formalizations. The goal is to minimize the expected energy of the problem Hamiltonian. Unlike many quantum algorithms that track a state vector, this paper uses a density matrix rho. This matters because the state is explicitly open. It interacts with the thermal bath, so mixed states are natural. Using the density matrix also lets the method naturally represent probabilistic mixtures, and degenerate ground state manifolds. The heart of the method is this master equation. The first term, the commutator with HT, gives the standard coherent quantum dynamics. The Hamiltonian includes the full problem Hamiltonian at all times, plus a transverse field term that promotes quantum transitions and helps exploration. That is an important distinction from standard adiabatic quantum annealing. In TQQO, the problem Hamiltonian is not gradually turned on. It is present throughout the evolution. The second term is the key novelty. A thermal relaxation operator scaled by a coupling strength CT. That drives the density matrix towards the thermal equilibrium distribution at the current temperature TT. So conceptually, the system is doing two things at once. Coherent dynamics spreads amplitude and explores, while thermalization shifts probability towards lower energy states. As the temperature decreases, the Boltzmann distribution becomes more and more concentrated in the ground state. This paper studies two physically motivated models of how the reservoir couples to the qubits. In the fast wire model, the bath effectively couples to the whole system collectively, and the state relaxes directly towards the Boltzmann distribution of the full problem Hamiltonian. This is the cleaner theoretical model because the thermal target is exactly the full system equilibrium state. In the slow wire model, each qubit couples locally to the bath. The transition rates depend on local effective fields, which are built from the current expectation values of neighboring qubits. These rates satisfy detailed balance, so the dynamics is still thermodynamically consistent. The trade-off is that the fast wire is more exact at the level of the full Hamiltonian, while the slow wire is more physically local and arguably closer to how hardware might actually behave. The slow wire model is also nonlinear because the rates depend on the evolving density matrix itself. The intended mechanism is a controlled quantum to classical transition. At the beginning, temperature is relatively high and the transverse field maintains exploration, so the state is spread across many configurations and it retains non-zero coherence. In the middle of the evolution, coherent dynamics and thermal relaxation compete. The transverse field keeps the state from immediately collapsing into a local minimum, while the thermal bath gradually favors low energy regions. At the end, temperature becomes low and bath coupling becomes strong. At that point, the Boltzmann distribution is sharply concentrated on the ground state manifold, so the density matrix becomes increasingly purified around the optimal solution. We track this process using two diagnostics, purity, which measures how mixed the state is, and coherence, which measures the size of the off-diagonal terms. So in our picture, good optimization means coherence early, purification late. To simulate these dynamics stably, we use a split operator method. A straightforward Euler method is problematic because the coherence commutator term can oscillate very rapidly, which forces a tiny time step for stability, and that becomes expensive and unreliable. So instead, each time step is split into two parts. First, the coherent part is applied exactly using the matrix exponential u equals e to the minus IH dt. Second, the thermal part is applied through an implicit update that is unconditionally stable for the fast wire relaxation. This gives a method that is exact in the coherent sector and stable in the dissipative sector. After each step, we also reinforce the defining properties of density matrix, hermeticity, positivity, and unit trace. This benchmarking is done on three different classes of Ising optimization problems. First are planted solution problems, which are meant to create rugged, unstructured landscapes with a hidden optimum. Second are random Ising problems, which are more generic. Third are max cut instances, which are especially relevant because QAOA was originally designed with max cut in mind. We test each class at 6, 8, and 10 qubits for a total of 9 instances. The baselines are QAOA at depth 10 with multiple restarts and classical optimization, and classical simulated annealing. The main performance metrics are the approximation ratio and the fidelity with the ground state. We also examine the full state dynamics through purity and coherence. So this is the main results slide. Across all tested instances, both of our models of TQQO achieve approximation ratios above 0.999 and fidelities above 0.9. In other words, in these small scale simulations, the method gets extremely close to the exact ground state every single time. QAOA, for comparison, falls quite rapidly by the time it reaches the 10 qubit case. For planted problems, the approximation drops to about 0.00666, while TQQO versions remain essentially at 1. For random Ising, it falls to 0.087, and for max cut, where it should be on more favorable ground, it still only reaches about 0.13 10 qubits, while TQQO remains near 0.99999. This corresponds to improvements of roughly 4 to 150 times over QAOA, depending on the instance. At the same time, classical simulated annealing, as implemented, also solves these instances exactly. So these results show promise against QAOA, but not yet over classical annealing methods. This figure is useful because it shows not just the final answer, but the mechanism we want to claim. In panel A, the fast wire and slow wire energies drop rapidly towards the ground state, while QAOA stays far above it. Classical simulated annealing gets there too, but via a classical trajectory. In panel B, we see the fidelity. The fast wire model rises quickly to near 1, and the slow wire model also approaches 1 just a bit more gradually. QAOA remains very low. Panel C is especially important. As temperature goes down and coupling increases, the purity rises while coherence decays. That is exactly the proposed quantum to classical transition. Early coherence for exploration, then late purification for convergence. And panel D summarizes the final energies. The TQQO and classical methods are essentially at the ground state, and QAOA is far away. So I think this paper is interesting for two reasons. First, it offers a genuinely different algorithmic philosophy. It removes the outer variational loop that makes QAOA difficult to optimize, and it gives a natural way to handle degeneracy because the density matrix can converge to a mixture over the ground manifold. Second, it suggests a different hardware mindset. Maybe optimization hardware should not always fight thermal effects, but instead shape and exploit them. But there are major limitations. The tested sizes are very small. Classical simulated annealing already solves these problems perfectly, although that may be an implementation thing. The fast-wire model is also costly to simulate because it depends on the full Boltzmann state of the problem Hamiltonian, and the QAOA baseline, while reasonable, is still only one implementation choice. So the fairest reading is this. This is a promising open system optimization framework, but not yet proof of scalable superiority. To conclude, the paradigm we've introduced today proposes that controlled thermal relaxation can be useful for quantum optimization rather than purely harmful. In our simulations, both bath coupling models perform extremely well across a variety of problem types, and the density matrix diagnostics support the intended quantum to classical transition. The biggest open question is whether this can scale on real hardware or with larger approximate simulations beyond the regime where classical methods are easy. So even if the current results are preliminary, the paper is valuable because it challenges a standard assumption in quantum computing, that thermal coupling must always be suppressed. And that's all I have. So thank you. And if there are any questions.
Thank you, Christopher. We can take one or two questions. We are on time right now. If there are no questions,
Yeah, Christopher, I want to ask one question. So, as far as this technique is concerned, so which quantum computing hardware where it has been tested?
So far we've only tested on classical normal computing methods. We haven't yet had access to quantum simulation specifically. As we go forward and as we look at more quantum simulation hardware, we would be expanding our problem sizes, and that's something we look forward to doing.
Okay, thank you.
Any other question? Okay, thank you, Christopher. It was nice talk. Let's move on to our next speaker. Danuja, are you there?
Hello, am I audible?
Yeah, you're audible, but voice is little lower. So can you, I don't know. I mean, first you share your screen.
Yeah. Is it better now?
Yeah, it's better, but share your screen.
Yeah. 1 second. Is it visible?
Not yet. Yeah, it's visible right now.
Okay.
Okay, so Danuja will be talking about erasure cost of a quantum process, a thermodynamic meaning of the dynamical mean entropy. Okay, Danuja, you may commence your talk.
Hi all. I am Dhanuja. I'm a PhD student in IIIT Hyderabad. And I thank for this opportunity to present our work. So I'll be speaking about our recent paper, Erasure Cost of a Quantum Process, a Thermodynamic Meaning of Dynamical Mean Entropy. It's a joint work with Himanshu, Swati, Vishal, and Siddhartha. So first, I'll start with the motivation for the problem. So we know that nowadays we are going to technological advancements where we are going to miniaturization of processes. And for this, to understand the energetics of the quantum processes, it is important. And here we are speaking about erasure and preparation cost of processes, where and through this we will come to know about energetic efficiency of the devices we will use for the computation. So first I'll start with, so to know erasure cost and those things, I'll first start with Maxwell's Demon problem. So Maxwell's Demon problem was given by Maxwell. It's a kind of a paradox, and it was given around 1850s by Maxwell. So it is a thought experiment. It says that you like consider a chamber which can be divided into two parts, and there is a trap door in between. You can see a trap door in between, a small door, and there is we consider a demon there, that is some being which can like follow the speed of the all of the particles inside the chamber, and and uh, and by knowing that it can close the door and open the door in such a way that it can eventually make the chamber divide the chamber into two parts, such that one part will have speedy particles and the other part will have less speed particles. This was a problem because according to second law, an isolated system should not be there should not be a decrease in entropy in an isolated system, and here it is an isolated system and it shouldn't be. Here we can say that entropy is decreasing, which shouldn't be happening. So this was a problem during that time, and the solution was given by Landover's principle. So Landover's principle said that any irreversible process increases entropy and it dissipates heat. So and here erasure is so this is Landover's principle about erasure, and erasure is a thermodynamically irreversible process. So the solution was that we have to consider the daemon also into our system. That is the daemon's memory also. The daemon has to follow all of the particles' speed, and it has to follow, it has to save all this information in its memory. So that also, when we consider to the system, it is consistent with second law of thermodynamics. And erasure, so the thing is, like, after some time, it will have to erase some bit of information from its memory. And this erasure will cost work, or it will have to do work to erase the bit because it's an irreversible process. And this is how the Maxwell's daemon problem was solved. So thus we understand that to erase a bit of information, we need to put some work. And that work cost is has some value. So these are all classical cases what I'm speaking about. This is all classical thermodynamics actually. So so first let me tell what erasure of a bit means. So erasure of a bit in classical case, it is like we replace the bit with a 0 bit. That is the erasure of a bit means, and it requires a work cost which is proportional to the entropy of the difference between the states we are erasing. So in quantum scenario, when we come to erasure, it means that whatever the state or whatever state qubit there is, we'll replace it with a 0, 0 qubit. That is the idea of erasure in quantum scenario. And there were results which said that the work cost to erase a state and replace it with 0, 0 also is proportional to the von Neumann entropy of the state row. Since it comes to quantum scenario, we'll go to von Neumann entropy instead of Shannon entropy. And there is another idea that what happens if we are trying to erase a subsystem, that is, there is a system and we are only trying to erase a part of the system. In that case, we are considering a bipartite system, and we are considering that we're erasing a part of the system, and then we can use the correlations between the subsystems to reduce the entropy and the work required to erase the system. So there the entropy value or the entropy function is given by conditional entropy rather than the von Neumann entropy. This was an eminent work by Lydia Del Rio in 2011. So now our question, what we were asking is that we know so what is a quantum? So we know quantum process, right? So quantum process is represented as a quantum channel in information theoretic point of view. So we are asking what is the work cost we'll have to put in to erase a quantum process itself. So this is the problem we are considering. That is, we consider the unitary extension of the channel, And A prime is the input to the channel, A is the output of the channel, E prime and E are ancillas, environment ancillas to the channel, and R is the purifying state. It is the purifying reference state to the input state psi array. Now, so here we can ask, what do you mean by erasure of a process, right? So erasure of a process, here we mean, what is that? Whatever the output of the channel is, we replace it with the 0, 0 state. That is, the channel is actually taken to a replacer channel, where whatever the state is, it is replaced with the 0, 0 state. Now there is so then we can ask, like, so when we consider a quantum process, does it have an entropy, right? So there is a paper by Gilad Gur and Mark Pillay, that entropy of a quantum channel. So there they have given entropy definitions for quantum channels. So they have given entropy definitions for min entropy, max entropy, von Neumann entropy, everything for channels. So we consider min entropy of channel here. So min entropy of channel is defined in terms of max relative entropy of states, actually the channel acting on the states. And here Ri is a replacer channel which replaces states with identity map. It can also be defined in terms of conditional min entropy of the state. Actually of the channel acting on the state. Now there is another idea, that smoothened min entropy of a channel. So smoothened entropy of a channel is the so here we consider an epsilon ball around a channel, and epsilon ball around a channel in the sense that the distance measure we are considering here is a purified distance, which is also in terms of channels. And we consider all the channels around the channel in the epsilon ball, and we see what are the entropies if you substitute all these channels, and we find the maximum value among them as the min entropy, smoothened min entropy of the channel. So our result is that this erasure cost of a channel, that is the work cost we have to put in to erase a channel, also is bounded by min entropy of the channel. So we take the smoothened min entropy of the channel, and with this probability. So this is using thermodynamic approach in the sense that we use the conditional entropy, the result I was showing before. So we use that idea here. There is a resource theoretic approach as well, through which also we get that the erasure cost of a channel, that is the work cost we have to put in to erase the channel, is proportional, or which is bounded by min entropy of the channel. And here we can find that preparation cost also we can find out. The preparation cost of a channel also is bounded by the min entropy of a channel. I can show it pictorially as well. In both cases, there is one thing we have to notice, that so I can consider this daemon is not the Maxwell's daemon, by the way. This is just some daemon. Okay, so this daemon is having access to E. So we assume that during erasure, the daemon has access to whoever is erasing, which has access to the environment of the channel. That is, environment means that we know the channel is noisy. So the information the channel loses is to the environment. So we are assuming that the erasure has the access to environment. So with access to this environment, the daemon is trying to erase A, that is the output of the channel. So this is the idea of erasure here, and we found that that is bounded by min entropy of the channel. And we find that there is an angel who is preparing the state, but it has access to R, has access to the purifying reference state of the system. So and both are bounded with min entropy of the channel. Now at zero error, the preparation and erasure cost of the channel is equal to so the entropy of the channel. It is proportional to entropy of the channel, and this is one thing we can also see from the following equation, that mean entropy of a channel is written in terms of fidelity between two different aspects. So here we can find that the mean entropy of a channel is, you can see it as the ability of the channel to keep the singlet state or keep the maximally entangled state. And that is what the first expression is showing. And second expression is showing that, so here we have to take the unitary extension. So here we are not taking unitary extension, we are taking isometric extension where we include the environment also into the channel. And so here what we are saying is it is the ability of the channel to decouple the system from the environment. That is, using S-min of n, using the mean entropy of the channel, we can see different abilities of the channel. So through this, so the first is like with the entanglement with purifying reference state, and here it is we are decoupling it with the environment of the channel. So you can see how the expression 8 can be seen through this also, these expressions also. And second expression is also explainable from the decoupling theorem of processes, which result we actually have given in the in our paper. I didn't include it because of the time limitations. So decoupling theorem is, so we find that decoupling of the channels also is bounded by the mean entropy of the channel. So that is how it is related to the erasure procedure. So now we go to examples of the quantity side. So the main result I have to show you is that how important or how mean entropy of a channel has importance physically or in thermodynamically. So here we take some examples. As if we take an isometric channel, we find that S-min of the quantity, the mean entropy of the channel is minimum, which means that zero overall work cost of erasure and preparation is maximum. This you can see from the work cost expression itself. So we know work cost of erasure there we assume that we have access to environment, and when we take an isometric channel, we take the environment into the channel. So we actually don't have any environment. So or you can see it like the channel doesn't lose any information to the environment. So since it doesn't lose any information to the environment, we don't have any information about the from the environment. So that is how the work cost of erasure becomes maximum there. And then there is replacer channel. Replacer channel replaces the state with a particular channel state, a mixed state. So here also you can see that S-min of n is maximum there, and the preparation erasure cost is minimum there. That also we can see because replacer channel is the most noisy channel. That is, it loses all the information about the state into the environment. And since we have access, or the eraser, we assume that have access to environment, so we can see that it can erase the state with minimum work. And there are two implications for PPT and NPT channels. So PPT channels, for PPT channels, mean entropy is greater than or equal to 0, and so thus erasure cost becomes negative. And S-min of n for NPT channels is less than 0. That is for NPT channels. With this, I'm concluding the talk by saying, so the main result of our paper is that one-shot erasure cost. So in all these cases, this is one-shot erasure cost and preparation cost of physical transformation is proportional to dynamical mean entropies. So this is the main result of our paper. We have also given decoupling theorem for processes. That is, we have generalized decoupling theorem for states into decoupling theorem for processes, and it is bounded by mean entropy of the channel. Now, future directions, we can see decoupling theorem for processes might have a lot of applications, since already decoupling theorem for states has a lot of applications already. So we are expecting that there must be some applications in for channels case also. And thermodynamic resource theory of quantum channels is something we can do, which we have already done that aspect of the future direction. with this, I am concluding my talk. Thank you.
Thank you, Danuja. Questions? Danuja, we have questions in the chat box.
Oh, let me try to see it. 1 second. Oh, it's yeah, so in quantum communication scenario, not in exactly quantum communication scenario, in quantum computing scenario, we can consider, so we know the erasure of a system can be used to reuse the qubit, in the sense that if we have a long computation and if we want to put in, we only need one qubit or one particular state till some time of the computation, and after that we don't need it to be, because during the computation it might have changed, we don't know what state the qubit is. So then what we can use, we can give this erasure work cost, and we can make the qubit 00 state again, and we can use or reuse that same 00 state into the computation wherever we need the ancillars. But but this is for the states case. So if we know the channel case, what we can use is like, since we know about the channel, so we can compute what in the channel case also, like we can substitute, like do the same thing with the channel in the place of the states. So that is one way. In quantum thermodynamics, it is this is a very interesting phenomena, because we have considered quantum processes here. So it's a general way than considering quantum states. So in that way, it is fundamentally a important result. That's what I have to say.
Okay, if there are no questions, let's thank Danuja. Danuja, you may unshare your screen.
Yeah, 1 second, sorry.
Our next speaker is Said Siddiqui. Said, are you there?
Yes, sir, I am here, sir.
Okay, you may share your screen. So Said will be talking about enhancing the charging capacity of many-body quantum batteries through Landau Zener driving.
Sir, can you see my screen, sir?
Not yet. Yeah, now we can see your screen. Okay, you may commence your talk.
Yes, sir. So, very good evening to all. I thank the organizers for giving me the opportunity to present my work on International Young Quantum Scientist Meet. So, this work is jointly collaborated with Dr. Manirul Ali, who spoke just now before. So, when everyone talked about quantum protocol and quantum communication, the basic idea of storing energy in quantum systems. So, that is when people like Alicky and Feins in 2013 first introduced the concept of quantum battery, where I can take a quantum system and I can try to store energy, and I can extract energy and make it use as work done. So that is that is when the term arises of what we call it as quantum battery. So the key challenge of such quantum batteries are to have very little input and maximum output, how much ever I can extract energy from that. So in this concept, so the basic thing came into mind is, how can many body interactions enhance this kind of charging performance? So what I have done was, I have taken a linear spin chain, like we call this as XY model. So this XY model have linear spins. I can prepare the state in a way that my initial state is the ground state of the system. So this is my Hamiltonian, where this is without charging field. So my first term talks about the individual spin states. Then this term talks about the interacting parts, like the XY interaction. So the parameters we have are the external magnetic field and the anisotropy parameter gamma, and the coupling strength between the spins and the total number of spins. So this GIJ, what we call it as interaction strength, we can even discuss this in terms of two scenarios where we talk about nearest neighbor spins and the long range spins. So I have discussed. Okay. So before going to that, what I'm trying to do is I'm trying to take a system. I call it as H0, which is my battery Hamiltonian. Then I am supplying my external field. So I'm supplying my external field. I call that as charging field. So that is V of t, where I try to make it as H of t and sum over sigma Iz. And I discuss two types of charging field. One I call it as Landau's inner driving, which is nothing but linear time dependent charging field. And another one is I'm trying to give a sinusoidal charging field. So in order to make sure how things work, I take the total Hamiltonian, whereas which is nothing but the charging Hamiltonian and the system Hamiltonian together to make sure that my system evolve unitarily. And this is a closed system on the whole, where my unitary operator have HC, which is nothing but the HC is nothing but the charging field and the battery Hamiltonian. So with this, what I'm trying to do is I'm trying to evolve my system. So my system is initially in the ground state, which I prepare as all spin to be in ground state or spin down state. Then I give an extra or what I can call it as a charging field. I make it to some other state. I don't know that is a maximum state or not, but I'm making sure that it is going to some other state rho of t. Then I try to extract my what I call here is work deposition. Now this work is based on work deposition. So rho of t h naught minus rho 0 h0, which is my work deposition. Or in terms of battery terminologies, I call it as charging. And I even calculate the average power, which is nothing but W of tau to tau. So the goal is to achieve maximum work deposition, and the average power has to be maximum in the optimal charging time. So this is my these are the results where we have fixed some parameters where my interaction strength and my anisotropy parameter. And the most important part comes here is when the challenging part comes here is when I take the number of spins, because when I talk about long range interactions, because nearest neighbor interaction meaning it is just interacting with say for example, if I have a site 2, then the spin will be interacting with site 1 spin and site 3 spin. So there are just two interactions. But when we talk about long range interaction, we are talking about spin 1, site 1 spin to site 8th spin. So that is one challenging task. And one more thing is when we do computationally, these are 2 power 8 cross 2 power 8 matrices. So you can imagine the dimension of the matrix. So computationally also it is challenging. And we can see from the results that by increasing the coupling strength, what happens here is my work deposition, or what we call it as charging, is increasing rapidly. So this result is for a nearest neighbor interaction. And when we talk about long range interaction, so you can compare that if we increase the coupling strength, the work deposition is also getting increased. But when we see the comparison where we have nearest neighbor and the long range, so long range is having more smoother version of work deposition compared to nearest neighbor, where it has so much of oscillation due to the local quantum coherence. And this is for various values of coupling strength. Then what we have done is, so this is like a comparison between how things are evolving with respect to both the scenarios where we talk about long range interaction and the nearest neighbor. And one more thing what we have done is discussing about this sweep rate, where we talk about this particular parameter V. This V is coming from the Landau's inner here, this Landau's inner driving, and that V has implication when we talk about adiabatic regime or non-adiabatic and maximum charging rate. So when we are trying to vary this in terms of exponents or order of negative exponent, -3, -2, -1. So we can see that for 10 power 1, like 10B, the work deposition is very high, whereas for other values of the sweep rate, we can see there is no much of work deposition even in terms of long range or nearest neighbor. So this makes sure that we want to be more in the initial or we can call it as non-adiabatic regime. And this is for work deposition for different values of V, where I'm increasing my V values. So B2, B3, 4B. So I can see that the work deposition is increasing rapidly. And the very most important thing is when we compare the nearest neighbor to the long range, so the work deposition having very smooth curve when we go for longer values of the sweep rate. So maximum work is you can see here from 87.5B, which is nothing but 2.3 times higher than the norm than the nearest neighbor interaction. So this is a very good result when we talk about long range interaction. And we want to talk about how anisotropy affects the system. So if you see here carefully, this gamma value, which is coming from the Hamiltonian of the battery, I just want to show a small recap where I have the gamma value here. So I'm trying to tune what happens to my battery Hamiltonian or my charging capacity when I change my gamma values to 0, 0.2, 0.4. So we can see how it is gradually increasing. The same goes for long range, and as we expected, for long range interaction, we have the more anisotropy, the more work deposition is happening. And we have even studied for in the number size. So if I increase the number of spins, what happens to the system in work deposition, in terms of work deposition, we can see that for n is equal to 5 spins, we have work deposition maximum as 45, around 45, and for 6 it is increasing. So there is a near linear scaling with system size also, we can see that. And one more thing what we have studied here is there in the battery Hamiltonian, we have a coupling interaction term. There we have G divided by modulus of I minus J power A. So that A, so this is like when we talk about gravitational potential and so on, so it will be like 1 by R potential. So that R power A, so that A is what we are talking about here. So if we talk about 0.51, 1.52, which one is most the more good in terms of work deposition, that also we have considered here. So, and one more thing what I have done here is when we talked about periodic driving, when we talked about V sine omega t, here what these graphs shows is I have compared my W max, like maximum work deposition, and the Landau-Zinner driving. So in some cases we can see not Landau-Zinner driving is always not Landau-Zinner driving is not always winning. Sometimes the nearest neighbor also winning in terms of periodic driving. So this is for these are the two different results where we talked about Landau-Zinner and periodic driving. And as you can see, the Landau-Zinner driving has a dominance over the periodic driving. And these are a W max result, not the work deposition. So I have taken up to 0 to 20 into 2000 cuts, and this is like the maximum out of all time. And so there is a gradual question comes, which protocol I should use. So what kind of driving I should use for quantum batteries, specifically in terms of one-dimensional Ising model or one-dimensional spin chain XY model. So here we have seen that for Landau-Zinner driving, the number of sizes, if it is more than 4, number of spin, if it is more than 4, and for long range interaction and high capacity storage and adiabatic like evolution, Landau-Zinner has dominance over the periodic driving. Whereas in periodic driving also, as you can see here, in periodic driving also, for nearest neighbor system, there is dominance for smaller system sizes and controlled energy input systems. So these can be used for quantum sensing applications. And these are some of the reasons why Landau-Zinner and long range interaction work so well, because it is like a coordinated system. As I initially said before, this is a collective synchronization where the site one spin 1 interact with almost all the spins together. And whereas when we talk about nearest neighbor, it just interacts with the adjacent spin sites. So that is why we can say that these are some of the important results where when we talk about Landau-Zinner and long-range interaction. So these are the conclusions when how things are being done. So this is the published work which I have presented just now. And for future directions, what we can do is, now we have taken a closed system. So in further, there are open quantum systems where we can discuss more on this open quantum batteries, and we can add dissipation system. And so this is like different. So I have taken just one-dimensional spin lattice. So we can take alternative spin configuration, and coupling strategies could be different. And beyond linear periodic, there are other driving fields. So most challenging part is the experimental realization, where the trapped ions and optical lattices. So how to make this into an experimental reality, that is a different task. And the extractable work. So here we have dealt with just the work deposition, like charging. So discharging work, we call it as ergotropy, where I can maximally discharge the work from a system, and the charging precision. So these are the open question and extension. So I thank the funding organizers, funding agencies for supporting the work. With this, I conclude my talk. Thank you.
Thank you, Said.
Thank you.
Question? Said, we have a question in the chat box.
Yes, sir. How can quantum batteries be implemented using superconducting qubits, trapped ions? So using superconducting qubits, there are many work being done, and even there are experimental realization of such quantum batteries. My part is on doing the theoretical aspects, and this is like a very basic system when we talk about, where we talk about spin, and anyone can easily understand how this simple one-dimensional spin chain could be utilized in terms of quantum batteries. So my work was based on that. And as you have mentioned, superconducting qubits and trapped ions, there are many works done on this specific idea of quantum batteries.
More questions? Okay, if we do not have any question, okay. We have one question coming.
Yes, sir.
Yeah. So Priyan Sharma, you can ask your question, or you type your question in the chat box.
Okay, so advantages of Landau-Zinner is, yeah, that is a very good question. When I started doing this work, there are many works already in quantum batteries, where there are people who have done similar work, where they took the charging field as a periodic charging field. Say, for example, step potential, or some other periodicity is there. But when I take this Landau-Zinner, what happens here is, I have the full freedom of time frame. When I talk about step potential or some other periodic potential, then the periodicity has to be maintained. But whereas this kind of specific Landau-Zinner driving, I just fix the driving rate, or we call it as sweep rate. Then I'm good to go with the experimental aspect. So the advantages of Landau-Zinner is, it is more and more towards the experimental reality. Whereas if you talk about any other periodicity, we have to make sure that the periodicity is maintained. Yeah. So difference between normal battery and quantum battery is, so basically whenever we talk about any quantum system, what happens is, the coherence, if the coherence is maintained, then I can preserve the quantum property. So if the quantum property is maintained, I can store energy, and I can extract energy in a very in a minimal system. Like for one dimension spin itself, I can store this much amount of energy.
Okay, Priyansh, do you still have a question?
Thank you.
Okay, thank you, Said,
Yes,
for
sir.
a
Thank you.
nice talk. Okay, you may unshare your screen.
Yes.
Sandeep, over to you.
Yeah, so I think since the second session will start at 7:30 and we still have 15 minutes left, so I think the participants can unmute, and if they want to ask question to any of the speakers of this session, so they can ask now also.
Even if someone interested want to discuss something in general, means we can make a informal discussion window now, because yesterday we are in crunch of time for questions. Now we have time, so one can ask or discuss, make comments. Even the speakers feel that means there something is left, they can want to say something, then we have.
Sir, there is a question in the chat
Yes,
box.
please
I want to
continue.
answer. Actually, the Landos inner driving is experimentally feasible, and it is a complete different experimental aspect, where people talk about two different quantum states having crossover between, or we call it as quantum transition between one state to another state, and there is a term called probability transition also being calculated. So Lando's inner, as of now, is a complete different aspect. But in terms of quantum batteries, we have done the first time we have done, and as it is already experimentally feasible. So, and even one-dimensional spin chain is also experimentally feasible. It is easier to make, but actually, when we go for experiment, we will know the experimental difficulties. But it is experimentally feasible as of now. Okay, so there is one more question. According to your research, what is the minimum approximate energy that quantum battery can produce, and for what type of work will that energy mainly be used? Yeah. So right now, the minimum approximate energy, as I have shown here, we can see that these work deposition are nothing but the actual work deposited. So we can actually measure these work using some appropriate units. I have used natural units here. So if we can use the proper units, or whichever unit we want to use, we can actually measure, and we can use these energy, and this aspect of quantum battery is nothing but to store energy and to extract energy. So the question is being asked, what type of work will that energy be mainly used? So say, for example, if I have a quantum system, and if I want to extract energy from that quantum system, so the very big challenge, I think everyone will agree, is to maintain the coherence of a quantum system. So the moment when I disturb the system, or the moment when I try to bring some other element, or even do a small disturbance, so the first thing which will go off is the coherence. So so the moment the coherence goes off, the quantum nature is being disturbed. So the extraction process, as you mentioned, what type of work that energy mainly be used, the extraction part is a separate topic of discussion, where we deal with open quantum system, and that even there we have to have some regulated form of Hamiltonian to discuss how we can extract the work deposited in the quantum system. We call there is one more term called ergotropy, where I can that means that I can extract how much energy I can maximally extract from a quantum system. How much energy I can maximally extract from a quantum system. So that we have to do in a separate way? So I hope that answers the question. So will a quantum battery make quantum process more expensive? So okay, fine. I will put things into perspective. Actually speaking, if you see the terminology, so in quantum thermodynamics, this terminology called quantum battery is nothing but I have a Hamiltonian, so which is nothing but I have a system, and I am trying to add a extra Hamiltonian, or we can I can call it as charging field. Okay, but it is an in general we are talking about an extra Hamiltonian, and I am trying to evolve my system from the initial density matrix to some rho of t, rho of 0 to rho of t. That's all. So rho of 0, and I'm making a unitary transformation, or if I'm dealing with open quantum system, then I have to evolve it in a different manner. But the point is rho of t, which is my initial density matrix, to rho of 0, sorry, rho of 0 to rho of t, and this like this evolution rho of 0 to rho of t, I'm trying to calculate the average difference. So that is what is that is what we call it as work deposition. Average difference, rho of t, the Hamiltonian system Hamiltonian, minus rho of 0 and the system Hamiltonian, which is nothing but the mean value of the energy between two different times. So that is what we call it as work deposition. Okay, so when you ask about more expensive, uh, you are talking about in terms of economically, or like in terms of quantum nature of the system. I don't understand that. I didn't get that. Okay, economically means like maintaining a quantum nature of a quantum system itself is economically challenging. So like there is nothing called room temperature. Uh, I don't know, but as of now, maintaining a quantum nature of a quantum system itself is a little bit difficult. Not little bit, it is really difficult. Okay, why you using Hamiltonian? Thank you, Sharmaji. Why you using Hamiltonian in quantum battery? So that's what I want to clarify, that uh, this quantum battery is actually a term, but it is nothing but the Hamiltonian, which is the system, and that system is what we call it as battery, because I'm going to deposit work in that Hamiltonian, and I'm going to extract work. So that is what a battery does. So what does a battery do? It is used to store energy, and that stored energy should be able to extract and make it into work. So that is what battery does. So we are dealing with quantum systems. So that is why we call it as quantum battery. Thank you. Thank you for the questions.
So let us thank, I think, all the speakers of this session and also the session chair for conducting this session. So next session will start at 7:30. So we have this 10-minute break. So in this 10-minute break, some informal discussions can happen.
So there is one more question. Can this be used in NISQ era devices? I'm sorry, I am not aware of uh, that devices. So I think I am not be able to answer that question, sir. So basically, decoherence will make the system's quantum nature to lose its quantum nature. So it will no longer, or I can say it will actually make the system's efficiency go down. So it will not assist in charging. Thank you. Thank you. Thank you.
So if there is no other question, comment, etc., means we can quickly, or if quickly tell something about yesterday. We had a very short introduction. I can take a few minutes because we have some time and move for something, some generic discussions and a bit about the organizing department. So as you know that this event is organized by Quantum Optics and Quantum Information Group of JP Institute of Information Technology, Noida. And here we have an interest in human resource development always. We started teaching very early, then wrote a book. And now we are planning a MTech program in quantum technology from the next semester. And apparently there will be other places also because the AICT has launched this program. AICT launched another program called Minor Degree in Quantum Technology, which we already offer. And there may be some of the minor degree students who are here. So just in case some of you are MSc student, or you know people who are MSc students, you are students, or even you are teaching in engineering institutes and they're BTech students who are interested to know more about it. So you can share this information that we are going to start MTech quantum technology, and probably we are not alone. Already IIT Jodhpur teaches such a program. Then there is a MSc in the related area at ISAR Pune, then at Quantum Hub. Then IISc teaches a MTech in quantum technology, and now there will be a couple of more institute from this year, and there are minor degree also, and even in the other way around means who are teachers and there are no such course, you can also think of starting such course. And this course will have a greater impact. Like already in this meeting, we have seen that there are 475 registrations, and out of them, majority is from India, and so it's amplifying. At the same time, there is a need also, when like in my right now, I'm looking for a JRF for my lab, and preferably I'm looking for someone means who have some training of optics, who can do laser alignment, etc. But getting a trained hand, especially in experiment, is pretty difficult. Another feeling which we all have when we enter the lab, that most of the equipments in the lab are from some other place. So like if I enter my optics lab, there is an optical bench which is from Hallmark. Everything else is from Thor Lab or Newport or companies like that. So some indigenous, although this is an international conference, there are participants from outside as well. Means when this is true for every country, that if there are indigenous technology, indigenous repairing, then time of research increases. So if somehow my laser become non-operative and I have to send it to Sweden for repairing, it takes a lot of time. So, and many things which we use in our labs are classical. We use oscilloscope, we use FPGA board, we use lenses, beam splitters. So final result is quantum mechanical, but the components are often classical and they have used in classical technologies as well. So that's a part of NQM also, and it's a desired thing that we build. People make startup comes up with good idea, good products, and indigenous products. I mean, it's not restricted to India, because there are colleagues who have joined this meeting from Malaysia, So it is same for Malaysia also. If there are colleagues who have joined from Taiwan, means things can be built locally, the local ecosystems can be developed. The growth of quantum technology in general will be faster. For that, we need manpower, and it's a small steps that we are going to start our own MTech in quantum technology program with a very small number of students. But for MSc students also, we teach some good number of courses. For BTech students, we teach minor degree. And such courses are increasing everywhere. Good books are coming. Now we see many undergraduate students who know a good bit of Qiskit, Python, and starting point from where we start discussing with our interns has been drawn out. So that must be observation of everyone. So if you want to share your observations, means you and or add something on my small feeling the time short general thoughts. So if you want to add your thoughts, you can, but otherwise we'll move to next session because it's almost time. So Shandip, I guess you can now introduce the session chair of the next session and move for the next session because it's already 7:29.
So welcome back for the second session of the day 2, and this session is devoted to quantum networks, and it will be chaired by Dr. Priya Malpani. Dr. Priya Malpani did her MTech from PhD from IIT Jodhpur, and then she was associated with JIIT as a postdoc researcher, and now she is working as scientist at C. Delhi. So Priya, over to you. Dr. Priya?
Am I audible?
Yeah, you are audible.
Okay. Thank you, Dr. Sandeep, for the introduction. Good evening, everyone. Welcome to this session on quantum networks. My name is Priya, and I will be chairing this session. So we have 5 excellent presentations today in this session. Each speaker will have 15 minutes for the presentation and 5 minutes for the questions. So let us begin with our first speaker. Our first speaker is Dr. Satish Kumar from IISER Mohali. His presentation title is Development of a Quantum Repeater-Based Network Simulation Framework. So over to you, Dr. Satish.
Hello, am I audible?
Yes, you
Hello.
are audible, Satish.
Okay. Thank you for the kind introduction. Let me share the slide.
We can't see you.
Okay, I will turn on my camera later. So can you see my presentation? Hello.
Yes.
Okay, so it is always nice to talk to your own group. So especially where you have done your PhD, and it is very the excitement become more enhanced when you introduced by someone who is very dearest and nearest to you. So the title of my presentation is Development of Simulation Framework for Quantum Repeater Network. So the motivation behind the talk is of course, with the throughout the year, the number of IoT device in the chip get increases exponentially. That also uh, exponentially increase the energy consumption. So we need some technology which is exponentially more computationally powerful. So that technology is quantum communication or quantum computing, so which leads to quantum internet and quantum repeater protocol. So what is the importance of quantum repeater? So there are two figures. On the left side there is no repeater, and the right side there is a repeater node. So when there is a no repeater, let us suppose x and y are two quantum memories, and small x and small y are the two optical pulses. So if the optical pulses and the quantum memory is entangled with some entangled state 5 plus, so our aim is to generate an entanglement between the end node, which is x and y here. So this will get uh, so the optical pulses, which is small x and small y, will get in intermediate for the Bell state measurement, which is BSM. then we will generate an entanglement between the node X and Y. So to do the Bell state measurement, two things are very much needed. One is the photon must arrive to the intermediate mode, and the second is the arriving the arriving time of both the photons from the neighboring node must be simultaneous. So if we estimate the generation probability of the photon which is generated between the node X and Y, this is given by PZL, which is e to the power minus L by L attenuation by 2. So this factor 2 is because of when you do linear optical Bell measurement. So out of 4 Bell state, you will get 2 Bell states. So this is why this PZL is equal to this exponential sum terms. And when you do so, because every time you not generate the entanglement in the first trial, so you need to do several trials to get the entanglement distributed between the node X and Y. So this average number of trial is given by TZL, which is the inverse of the PZL. So when there is a repeater node, then you do the same entanglement generation things, but now you have a repeater node. So the advantage of giving a repeater node is now your average trial will improve with the square root terms, and this is how you can see you will have 2 to the power 2 e to the power L by 2 L attenuation. So this is how you feel there is an importance if there is a repeater node. So there is an advantage to do the quantum communication for the long distance. So if you talk about the network architecture, so the quantum network architecture always have a three layer. It is a infrastructure layer, logical layer, and the service layer. So in the infrastructure layer, you will have all the physical nodes and the fiber connection. Now you have to choose key between which two path you have to do the communication, and then you choose a suitable path or a optimal path for that. That is called network topology. And after that you have a service layer where you can do all this thing: entanglement generation, swapping, and entanglement verification, and so on. So when you realize the quantum repeater, so you will come across several parameters like entanglement generation fidelity, photon arriving probability, Bell state measurement fidelity, decoherence of a qubit because your qubit can square it, and entanglement distribution time is also very important. So, and for detector, it is detector efficiency and dark count. So here the three losses has been modeled, which is fiber loss, memory loss, and detector efficiency. So initially, when you start with the entangled state, rho 1 and rho 2, rho 1 is distributed between A and C node, and rho 2 is distributed between C and B node. So first we introduce the fiber loss using the amplitude damping cross operator, which is Ki here, and then you introduce memory loss using the Pauling-Nernst Z-gate. And after that you introduce the detector efficiency, because after that you will do Bell state measurement, then you introduce the detectorness. So your state rho 1 will evolve like rho 3. And currently we are ignoring the entanglement generation, fiber coupling, and memory loading. This kind of thing we are ignoring in our simulator. So these two losses, where is loss error, which is fiber loss, and the operational error, which is gate error and things like that. If the loss error and operation error, if both error is suppressed using the probabilistic approach, then we call it first generation quantum repeater. If the both losses is if fiber loss is suppressed using the probabilistic error, and operational loss is suppressed using the a deterministic approach, then we call second generation quantum repeater. If the both loss is suppressed with the deterministic approach, then we call it as a third generation quantum repeater. So we are making a simulator, we call it as a connect, which is quantum network and communication toolbox. So this is how our simulator currently looks like. Of course, there is a scope of improvement always. So this is the GUI of the simulator which I created. So we called it connect. So first you choose the distance of up to what distance you need to communicate, then you choose according the number of repeater. When you increase the number of repeater, you can see the fidelity get increases. So then we have a option to choose the topology. So currently we are working in the linear topology, but of course I introduce with a star network topology and other topology also. And then you need to key what kind of entanglement distributed between the end nodes. So we have an option, there is a Bell state, and there is, you can optimally also introduce your own distributed state. Then currently what noises we are taking care of in our simulator is entanglement preparation time, memory loss, and detector efficiency and dark count. When you enable noise parameter, then you can see under what noisy condition your uh, result, your final output is. So currently output which we are producing is final entangled state and fidelity. So you can see there are 3 tabs in the simulator, which is simulation, plot, and documentation. And the documentation, in the documentation tab, you can see whatever the function we have defined. You can see the documentation of that. So the key feature currently of our simulator is to quantum. So first is the quantum system simulation, where you can solve and study the complex quantum mechanical problem. And the second is quantum channel analysis, where you can model different type of quantum channel, or you can check the which channel is best for the network. And third is quantum repeater network simulation, which I have shown. So to make a simulator, you need first define the basic function which is used to make a simulator. The basic function is the inner product, generate random number, Bell state generation. So this is the basic classes which is defined, which is Q. QP is for quantum products. Q class is to generate, is to get us density matrix or normalize the state. And is a statement kind of a thing. So if is state, so your statement is true if the state is in the vector form. So this is how you can call our a package from your Python interface. So we called it from so my package name is QR network currently. So from QR network I imported this class, and I can do this kind of a function to generate the state and see the output. So of course we have to define the entanglement based bit class, because we are generating entanglement between the nodes. So we have to check whether the entanglement distributed between the node is how much entangled. To check that, we have defined the ebit class. And this is how our final quantum repeater function look like. So this is the flow chart of that, where you provide us a shared of state, and then our simulator will check whether the provided state is a Kate vector or entangled. Whether it is a Kate vector and entangled, if it is yes, it perform entanglement swapping between the nodes and give you a output as a obtained state and fidelity. If it is not a Kate vector, then it will check whether it is a density matrix and it is entangled. If it is entangled and a density matrix, then again it perform the entanglement swapping and give you the output. If it is not, then the process stop and you will see an error. So in the future, we want to incorporate the entanglement generation, fiber coupling, and memory loading, this kind of thing. Also we will add the entanglement routing protocol. We will do the quantum error correction or entanglement distillation protocol. We also in the process to define a metric to rank the which network is good and bad. So this is for, we define the metric of the rank of the quantum repeater network. And our code is currently available, but it is not public. It is available on the GitHub. And we will also make our package so that ready, so that anybody can install and use. So we will make some, if you do pip install our package, then you can install and use it in a network. So these are the references, and thank you. Hello.
Thank you, Dr. Satish, for the wonderful presentation,
Yes, sir.
especially that simulator part. So we have now 5 minutes for the questions. So any questions?
So if the speaker wants to add some more comments, you can utilize the time.
Satish?
Oh, so I
You
don't
want
have
to
any
add something?
comment. No, no. So somebody has raised his hand.
It's Pritik Jain
Okay.
want to ask. Yes.
Ritik, please continue.
Pritik, you may type if you are not able to speak. Mic.
There are some questions in the chat room also. Keep
So
the
it
chat.
is, have you published? No, it is not published. We are writing. So it is not in the shape to publish. If we add some more thing, then we will publish, of course.
Hello. Hello.
Yeah, hello.
Am I audible, sir?
Of course, you are audible.
Yes, you
Yes.
are. Please continue.
Yeah. Sorry, sir. Sir, I wanted to ask, like, I am also currently working on like a development of QKD simulator. So
Okay.
in your simulator, means are you simulating like individual qubits? Like, are you developing an analytical simulator, or is it a like a discrete event-based simulator? Like,
No, actually, this qubit generation part is not yet done, but yeah, we are thinking about it. We will do this. So we are now, our some other group is doing the qubit generation part. So we will after some time we will incorporate those in our simulator.
yes.
We have one more question in the chat box. Can you kindly comment on the complexity in terms of the resource cost, such as memory time of the simulator?
So complexity in term of the, okay. So of course, so this memory part is currently whatever the memory part we have incorporated is very abstract, because it is just we are using the decoherence effect of the memory. So in the very detailed scenario, so we are building some three kind of memory. But one is some what is called EIT based memory, and second is called some DLCZ protocol for something protocol for generating the memory. So when this can be done, then more complexity can be added to the simulator. Currently, this is just abstract memory kind of thing.
One more question.
Yeah, for
Also,
higher dimensional, of course, there is a plan. Like in first, we will build for the two-dimensional. Then, of course, we will increase to the higher dimensional, but not currently. Okay, I think.
thank you, Satish.
Okay, thank you so much.
Okay, now let us move to our next speaker. Our next speaker is Precious Ogabonda Amadi from University Malaysia Paris. His
Yeah,
presentation title, yes, his presentation title is Quantum Key Distribution with Spectral Amplitude Coding (OCDMA) for Multiple Access Network. So over to you, Precious.
Can you see my screen?
This is still opening, means it's there, but now it is visible, but it's not full
Yes,
screen. You can
your
make it full
screen is
screen.
visible.
Can you see my screen now?
Yes, yes, it's proper. And if comfortable, I
sorry.
would like to request all the speakers to keep their camera also on.
Okay.
If it is if
Okay,
you are comfortable, keep your
immediately.
camera on and please continue.
Okay. Let me share my screen. Can you see my screen?
Continue. You are visible. Your screen is
Yes.
visible. Everything is
Okay,
fine.
okay. Oh, my name is Precious Obunda Amadi, and I want to thank the organizers for this opportunity. I'm a PhD student in University Malaysia Police, and my presentation is one of our papers is published last year. It's on quantum key distribution with spectral amplitude coding, OCDMA. OCDM means optical code division multiple access or multiple access network. Now, basically, because of the high demand the high demand in traffic data transmission for a multiple access network, it is required that the network have high speed, is reliable and secure. Why are interested in security? For a secure transmission, secure communication, where it's expected that the channel is authenticated, the keys that is generated will also be used to encrypt and decrypt the data that is transferred between the transmitter and the receiver. Now, we're all aware now that the current state of art that can actually ensure transmission is a quantum key distribution, where a sender, a legitimate sender, transmits data to a legitimate user, and even with an eavesdropper armed with the sophisticated quantum technology, won't be able to intercept the keys without disturbing the system. And of course, the seminal work was done by BB84, by BB84 protocol, which is done by Bennett and Brassard. However, the existing communication infrastructure allows for multiple users transmitting data at the same time. So it is required that OCD and QKD will need to scale to meet the current demands. And in 1997, Townsend successfully realized the experimental setup for QKD being integrated into existing infrastructure. Here, he used two channels, the quantum channel, which is the O band, and then the C band, the classical channel, to make this realization. And this led to further development of QKD in multi-user network. Now, when in multi-user network uses the multiplexing scheme where multiple signals are combined into a composite signal. And there are different schemes that realizes this. We have the time division multiple access, where each user is allocated a specific time. We also have the frequency or the wave division multiple access, where each user is allocated a specific wavelength. And then we have the code division multiple access, which is our interest. Now, the WDM multiple access there are a lot of research contributions that have been done, even in terms of experimental realization and whatnot. However, its system basically has its own demerits. We talk about insufficient bandwidth utilization, where in a busty channel, a particular band is long stream of bandwidth. Some channels are idle while some are busty, and then we have strict wavelength synchronization. Now, OCDMA leverages on this disadvantage to come up with its own scheme, where each user is allocated a unique address code, which uses to transmit data. And in that system, we have advantages of the spontaneous data transmission. The issue of strict synchronization has been addressed, and then there's bandwidth maximization in the system. Now, our interest is in the encoder. The encoder in every OCDMA design, either in coherent or incoherent detection, what is the unique thing that we bring there is the encoder structure. The encoder structure comes with a specific property of having low correlation and then also high autocorrelation. And this is the first point of design in our architecture. So we first designed the encoder called the block shifted circulant matrix code, which is zero cross correlation code. The zero cross correlation code in this case, you see that the ones here represent transmission, data is being transmitted, while the zeros are no transmission is going on, and the rows are the users, and then the columns are the wavelengths. So you see here, for all of them, they are all 0, 1, 0, 1. So there's no overlap. When there's one attached in between this column, rather, you're going to get overlap. So our code design ensured that there's no overlap in it. And then the code weight, which is another property of the encoder, which is the number of ones for each K users in the system. So in this particular design, we had 3 users, 3 code code weights for each of these spectral bandwidths that we are designing for this system. And this paper was published in IEEE Access. Then the major our work was now integrating QKD into OCDMA. So borrowing the ideas of Townsend, in this case, the normal wave division multiple access would have had a QKD encoder, and then with in C band, in O band rather, and then the C band is classical signal where they are muxed and then transmitted. Here, the innovation here is we are introducing an encoder. Now, in OCDMA architecture, inherently it has its own security advantage where for an eavesdropper would need to have to decode the user sequence that is attached to that particular user. So introducing OCDMA, introducing the encoder now brings an additional security into this system. Now, in this case, what happens for a quantum signal that state is being prepared using a weak coherent pulse, a coherent state rather, and then it's transmitted to the encoder. The encoder acts as a beam splitter-like operation where it only filters or transmits just the signals where it has only just one, like this is one, and then for the first user, and then for the zeros, it blocks that photon that is coming in. And then with the classical signal, they are all muxed together, and then they pass to the star coupler, which now transmitted to the receiver, which is through the same process. It is now demuxed, and the match decoder it's used at this point to receive the signals, and then this decoded the same protocols that works in BBAT, QKD protocols. Now, in this case, for realistic settings, we have to take note of first. We have to take note of the passive elements that are here, because we are trying to model this system for a realistic setting. So here we looked at the transmitted signals, we looked at the average transmitted photons that is being distributed. Of course, the ones that have been activated, and then we took note of the channel loss. This paper was published in Journal of Optical Computing and Networking. Now, in our analysis, we made use of a decoy set analysis. Of course, we obtained the key rate. Our interest in this analysis, it's in the background noise contribution. This is where the encoder comes into play. Since we are making use of a zero cross correlation code, the encoder contribution to the background noise at code level is being eliminated because it's in zero cross correlation. While at the other end, it is the crosstalk, is spontaneous Raman scattering and forward mixing, that where they will find other contributions from what there is in terms of scalability. Now we looked at the impairment sources. We looked at the crosstalk noise, but the crosstalk noise is actually a device imperfection where quantum signal can actually leak into, or classical signal can actually leak into the quantum signal, creating false detection. Also looked at the spontaneous Raman scattering, spontaneous Raman scattering, where which happen in the fiber medium, where there's scattering from a higher frequency to a lower frequency. Of course, with classical powers that's coming with high frequency, it tends to fall into the quantum window and then creates false detection. And then finally, look at the four-wave mixing. Four-wave mixing happens in the classical band only, where there are interacting channels. Two or three interacting channels can create a fourth one, also creating false detection. Having analyzed this, we take our concern here is in terms of scalability. Now, first analysis we did was look at the power launch across these noise sources, and we noticed that for a very high power, up to -10 dB, the impact of four-wave mixing is felt in our model. However, as it goes towards -50, lower than -50, we start seeing the impact of crosstalk as expected in literature. So what's the take home here is that whenever you are designing your system, you have to take note of the power management to achieve a maximum performance of your Circle CDMA QKD system. Next, we looked at CK parameter for different CK rate for different parameter. First, we looked at our mean photon number, and we see here that at 0.5, we achieved a maximum performance of the secret key rate. At 0.8, there was a drop, which is likely due to multiphotons that can happen in the system. So for the rest of our analysis, we adopt 0.5 a mean photon number. Furthermore, we looked at, we compared it with quantum bit error rate. And for the secret key rate, we achieved a distance of 58 kilometers. And this quantum bit error is within 11 to 14%. For the conventional BB84, we already know that it gives you the quantum bit error rate is 11%. But in Sakani 2008, in their study, they state there that quantum bit error rate for decoy set analysis and for some other protocols can get up to 14%, which aligns with our results. And finally, we looked at the secret key rate for the different user and code weight configurations, and realize here that once the code weight, the user K is higher than the code weight, we achieve a maximum configuration. So all these are insights this model brings into in designing SACO CDMA for realistic use. And finally, we looked at the spectral efficiency. Of course, we already know that WDMA QKD is already existing. So we have to look at the trade-off at this point to see at what point is this SACO CDMA better than the WDMA. WDMA, if you go back to our system, the model, once the encoder is just one, you have only just one spectral with code weight here. You see here that it just behaves like a very the normal WDMA that we know in WDMA QKD that we know. So sorry. Now at this point we see that when it is one, it gives us WDMA when the weight of the code weight is 1, and it achieves a longer distance than the OCDMA 2 and 5. However, in terms of fiber length, when you look at in terms of scalability of number of users or channel, at short distance, at small low number of users, the OCD, QKDB, and WDMA have a better performance. However, when it gets to a very high users, they all behave the same, they converge together. If OCDMA have a better performance to WDMA in terms of security, in terms of there's no bandwidth bandwidth maximization, and then there is no strict synchronization, band maximization in the system, then OCDMA seems to be a better option when you have to sacrifice distance for scalability. So that's what our result was able to achieve. And finally, we've shown here that we can actually spectrally encode quantum signals in a multi-user network, and then using the zero-cost collision code, you can eliminate interference in the system. We also took note of that in the system design, the power we want to have the effect of crosstalk begins to emerge once the power begins to get lower than 50 dBm. And also finally in design, you have to take note of the scaling, the code design, the power management to achieve a robust power system. And for future use, this work was done using a discrete variable quantum key distribution. We intend to move forward to using continuous variable and analyze the system as well. Thank you.
Thank you, Precious, for the excellent presentation. So the floor is open for questions. We have questions in chat box.
You should check from comment box.
Okay. You said what?
We have questions in the chat box as well.
Okay, why do we use
Why do you?
No, what happened at this point is basically in we want to know how the power launch for different power capacity behaves for different at different times for the empowerments of noise. In SACO CDMA design modeling is usually 10 minus 10 dBm, which is quite high. So we had to vary from 10, and we kept going. As we got to 50 minus 50, we discovered the impact of crosstalk noise in the system. So basically, we know four-wave mixing is quite strong. It can actually degrade the system. So going down basically going down to -50, we start seeing crosstalk noise, and four-wave mixing starts getting the impact becomes lower. So it's just something analysis we found out the discovery we made in our analysis. Sorry.
One more
Would
question.
you like
Would you like to explain about other QKD techniques?
Oh, okay. What we actually used here is decoy set analysis. So we've not actually tried other ones in the system. So we probably hope that will be for future work. Like I mentioned, we also want to try using continuous variable. How do you
Like
improve the system?
wavelength
for-
division multiplexing WDM QKD.
Please, come again, please. I didn't get you.
Wavelength division multiplexing WDM QKD wave split like something wavelength split.
Sorry, I didn't get the question. Wavelength, what?
Maybe you can write the question in the chat
Okay.
box.
Okay.
How do we improve the system for 100 kilometers? Like I mentioned, to obtain a robust system depends on the user scaling and then the power management. So from our analysis, obviously we see that once the power gets lower and then our the code weight gets smaller, we can increase our distance. A longer distance can be achieved. But at this point, what we used in our analysis was at 30 dB. So at 30 minus 30 dB, that's what we achieved 58 kilometers.
There is one more question. Can we use QKD for security IoT device, low power device?
Oh, security. Okay, it all depends on how QKD can effectively be integrated into the IoT infrastructure. If it's yes, QKD works for low power device, true. But if it's successfully integrated into the IoT infrastructure, it can also be used, yes.
Any other questions? I think there is no question. So thank you again, Precious.
Okay, thank you.
So you can unshare your screen. Let us move towards our third speaker, Mr. Sudeep Chakraborty from SN Bose National Center for Basic Sciences. His presentation title is Non-Locality in Continuous Variable Quantum Networks. So over to you, Sudeep.
Yeah, can you hear me?
Yes, Sudeep.
Yes, you are audible. Please
Okay,
share your
okay.
screen.
Okay. Okay, is my screen visible?
Yes, your screen is
Hello.
visible, but it's not the
Okay.
it's not the slide. Means okay,
Yes.
now it's better. Make it full screen.
Okay, first,
And
is it fine
if
now?
possible, switch on your camera also.
Yes,
Then
it
the
is
recording
visible.
happens immediately.
So I don't know the strength of my Wi-Fi.
Okay. So then you continue. It's better then.
Okay, first I thank the organizers for this opportunity. Today I'm going to talk about non-locality in continuous variable quantum networks. And this work can be found in arXiv, and the arXiv number is here. If anyone is interested, he or she can see the paper. And this particular slide is made by ChatGPT anyway. So I will start with a brief recap of Bell non-locality, which is named after this famous physicist, John Stuart Bell. So in the simplest scenario, we have two labs, one to Alice, which I denote as A, and one to Bob, which I denote as B. And there is a source that creates two particles and send one to Alice and the other to Bob. And Alice and Bob, they both have some measurement choices, which I denote as X and Y. And after measurement, they get outcomes as A and B. Now, the question is, after the measurement and finding the outcomes, the joint probability statistics that is given by P, probability of getting AB given XY, can this be represented using a classical variable lambda, which is also called a hidden variable? If there is a hidden variable model, we call that local. If there does not exist such a model, we call that non-local. Now, it is not always possible to find such hidden variable description. Rather, one can look at certain inequalities. For example, I can talk about a simple CH-SH scenario, and that talks about the two input to output situation. And here, all these E functions, they are the correlators, A, B prime, they are different outcomes after measurements. Now, for local cases, it is upper bounded by 2. Now, for non-locality, it has to be greater than 2, and it can reach up to 2 root 2 in quantum theory. Now, is it just merely a description of non-classicality? No, it has found many applications. For example, I have listed some like quantum cryptography, communication complexity, randomness generation, and so on and so forth. And not just that, in 2022, 3 scientists, Aspect, Clauser, and Zeilinger, they won Nobel Prize for the establishment or experimental observation of Bell inequality violation. Now, here I must note one point, that one can see that this inequality is linear, which will help in the next slide. Now, in a general Bell scenario, there can be more than 2 particles, but the restriction is there is only one source, and that leads to convex correlations and linear inequalities to check locality or non-locality. Now, one can go from this scenario to something that is called a beyond Bell scenario, and that is the network scenario. Here, we have multiple sources, and those sources are independent. So if you want to assign some classical variable, then you have to assign different names like lambda 1, lambda 2, and so on. And here, these points, I can call them as nodes, and they have access to more than one particle, each coming from different sources. And the point is, in these nodes, one can do more powerful measurement. For example, if in one node, one can have 2 particles, he can do entangled measurement, something that is used in repeaters. But here my demand is to check non-locality. So the point is, in a network scenario, the correlation sets are not convex anymore. And also, if one wants to check locality or non-locality, one have non-linear inequalities. So the situation is difficult. But obviously, the hope is that one can find new forms of non-locality in this beyond Bell scenario. Now let's talk about some known network structures, also called as topologies. For example, the linear chain structure, where the parties in the edges have access to one particle, but in the middle nodes, there are access to 2 particles to each node. Now, he can do entangled measurement as well, or he can do any joint measurement on those particles. In the triangle scenario, there is no such edges like this one, and each node has access to 2 particles, and it's a closed scenario, but I'm not going to talk about this triangle network in this talk. In the star network, there is only one node, and this middle lab has access to 1 particle created from each source. So he can do a very strong measurement, and the edges, there is access to only 1 particle to each. Now, I'm talking about continuous variables. So what do I mean by that? I'm not going to into detail, but for completeness, for example, I'm talking about the same particle, but a particle can have different properties. Now, if I talk about spin of say, an electron, there can be only two possible outcomes, plus up, minus up, or up, down, whatever you want to say. But to describe the situation, we need a two-dimensional Hilbert spaces, and the outcomes are obviously discrete. So that belongs to the discrete variable situation. Now, if I talk about some other property like position, momentum, or vibrational degree of freedom, then there can be infinite possibilities, and we need an infinite dimensional Hilbert space, and such situations belong to continuous variables. And I'm going to talk about Fock basis, which is nothing but the eigenstates of quantum harmonic oscillator, or the number eigenstates. All the states, I will represent them in Fock basis initially. Now, what are the advantages of CV? The first and the most important point is known as unconditionalness, and it is a valuable feature. Quantum states, such as any entangled state that emerge from nonlinear optical interaction of a laser with a crystal, they emerge in an unconditional fashion, and that is hard to obtain in discrete variable situation. And also, continuous variables has a direct compatibility with optical implementations, and it is also useful in long distance communication, making it suitable for quantum repeaters. But I talked about something about the state. I talked about the scenario, but I need some measurement now. So I'm not going to use the known quadrature measurements here. I'm directly picking something from the Pauli matrices. Pauli matrices, these act on qubits in a two-dimensional Hilbert space, and they follow the SU2 algebra that you can look here. A straightforward strategy to go to higher dimension with the same algebra is to use more blocks. For example, if I write two Pauli matrices like this one, it acts on a four-dimensional Hilbert space. But this sigma I star, it is again dichotomic because we are interested in the eigenvalues or the expectation values. So there is only +1 or -1, and they follow the same algebra. Now, instead of 2, if I go to infinity, now we are using infinite number of blocks. Then what we get is the pseudo-spin operators, which are also dichotomic, like you get two eigenvalues +1 or -1. They're degenerate, fine, but I'm not interested in the degeneracy. And they follow the same algebra. So there, one can say that there is a mapping, that 2-qubit state with spin measurement, and also that CV state that is written in Fock basis with the pseudo-spin measurements, which looks like this, written using the Fock basis. So we have defined some structure of state, the measurements. Now we need some inequality. So for star, the inequality looks like this with two types of correlators, I and J. And one can obviously see that this inequality is nonlinear. And how we develop this correlator I, it depends on various A measurements, and they are nothing but some pseudo-spin measurement along some direction. A here is a 3D vector, and B0 is a joint measurement, and it acts on n particles. Now the J correlator, that is similar to I, but there can be a negative sign in front of some terms. Now B0 and B1, that looks like this. There is a product, so one can obviously see that these acts on n particles. Now for chain, if you can remember, there are like some nodes in middle, and they have access to two particles, and the parties in the edge has access to one particle. Now, in the edge, one have this type of measurements. So here again, A prime, C prime are just 3D vectors, and S is the pseudospin measurement. Now, in the middle nodes, I am restricting to some product measurement that looks like this, SZ, tensor SZ. For the I correlator, and for the J correlator, I will use SX tensor SX. Now, it is somehow important because it is also the partial Bell measurement. One can always write a CV state using the eigenstates of the parity space, also the pseudospin measurements or pseudospin operator, and one can find that after defining the parity eigenstates, one can show these as some sort of partial Bell measurement in infinite dimension. So the first case study I'm going to do with is with the two-mode squeezed vacuum, that is a Gaussian state. And it looks like this, where lambda is equal to tan h r, and r is the squeezing parameter. Now, what we observe that with increasing squeezing, we get more violation, and that is not counterintuitive. That is something obvious. What is interesting is that if I consider chain network, then the number of modes, if that increases, we get lesser violation. And that is also somewhat intuitive. But when we go to star network, then the number of states that we use in a star network, that does not matter if the states are identical. And it coincides with the two local scenario, also known as the bilocal scenario. So where we have two states and only one node. And bilocal scenario is the most simple scenario in both chain and star network. But that is non-trivial at the same time. From the next slide, I'm going to talk about the bilocal scenario only. So I talked about two-mode squeezed vacuum, but what about considering it with some thermal noise? So it can be considered using a noise model like this, where beta is the inverse temperature, and it is well known and well used in the literature. In the first plot, I have the colors. Colors represent the bilocal quantity, that S quantity, and it is plotted against P and K. P is the mixing parameter and K is the squeezing parameter, that is tan H2R. And this red line actually separates the local and non-local region. So there is nothing more here in this plot, but this plot is interesting. So here we plot the bilocal quantity with the inverse temperature. So more the beta means the lower temperature, and lesser the beta means higher the temperature. And we were able to show a condition between the squeezing and the mixing parameter, that if this criteria is satisfied, then whatever be the temperature it is, with increasing temperature, the bilocal quantity will decrease. But if this is satisfied, it will never diminish. It will never become local. So it is something counterintuitive that we found. Now, in the next slide, we are going to talk about introducing some non-Gaussianity using some non-Gaussian operation. That is, we are going to introduce using single photon subtraction. Mainly, we are going to consider three situations. Asymmetric subtraction, that means till now we are considering two-mode states. In the asymmetric subtraction, we apply the subtraction on one mode. In the symmetric subtraction, we apply a subtraction on both modes. And in the coherent superposition, we use some sort of superposition of these asymmetry subtraction. And the state prepared looks like this, but you can also not consider looking at these right now. Anyway, this 1 and 2, they say that A1 means we consider this operation in one state, and the other state in the bilocal network, we keep it two-mode squeezed vacuum. And A2 means we do this operation on both the states. And 1, 2 is same for all these three configuration. So what we see that when we apply this operation, we get some increase in violation, and that is somewhat again intuitive, but what is not intuitive is that using the coherent superposition of subtraction, we get something very non-peculiar. That is, we get maximal violation that is exactly equal to 2 root 2, the quantum bound, at zero squeezing. And the question is why? So again, this question is there. The question is why. If we look at the specific state, and if we go at the zero squeezing, we get the Bell state in 2 dimension. And the point is, it is specifically giving the maximal violation because we are using the zero spin measurement. And here, zero spin measurement can act on qubits as well because it is in blocks. It does not matter on which block is acting. And finally, I have 2 more slides. So till now, we were talking about theoretical aspects, but it is difficult to implement a pseudospin measurement in experiment, but there is a bypass. So till now, we are talking about single mode multiphoton space using the Fock basis, but there is isomorphism with the single photon multiple mode electromagnetic space that is obtained using the wave function picture in the position basis. So it can be represented using some eigenmodes that is represented using phi nx, and this isomorphism can be observed using this representation. That is nothing but the position representation of K10. Now, there is a specific choice of phi nx that I can take as the harmonic Gaussian function with this beautiful property of parity. That is, the even modes with 2n are even, and the odd modes with 2n plus 1 are odd. There is a negative sign, and which leads to some definition of parity. That is, one can write the wave function in 2 parts. One using these even parts, which is even, and a superposition with some amplitude with the odd parts that is with that belongs to the odd parity. Now, I need the pseudospin measurements in this space. Now, in the spatial representation, the pseudospin operators look like this. This mathematics may look difficult, but it is quite easy if someone looks at the original structure using Fock basis. That is nothing but replacing these modes, placing these modes in place of those K10s, and they are finally plugged in as.
Sudeep,
okay.
you have 2 minutes remaining.
Okay, I will complete. Okay, so these functions will be inserted as some impulse function in the position basis, and upon integration, one will get the pseudospin operators. Now, obviously, these parity, they lead to some experimental proposal. So in this proposal, I have 2 elements. Mainly, this is the bilocal scenario, and I have two photon sources which generate 2 photons each. And first, the photons go through parity rotators that I'm not going to into detail, but that actually introduces relative phases between x greater than 0 and x less than 0 halves of the transverse plane. That actually acts as a SO2 rotator. And finally, the parity analyzer, it actually acts as a dichotomic measurements, breaking the photon in not actually breaking. After this parity analyzer, the photon actually goes to either one of the detectors. So after detection, the final task is to find the coincidence counts, and one can find the correlators E, which are the elements of the IJ correlators. And after calculating the IJ correlators, one can conclude about the non-bilocality or bilocality of this system. So in short, or in conclusion, we proposed a scheme to observe non-locality in CB networks using the pseudospin measurements. We also gave some examples using Gaussian and Gaussian resources, Gaussian states. And finally, the striking feature that you showed, that maximal violation can be found at zero squeezing after the coherent superposition of subtraction operation. And we also proposed an experimental proposal to observe network non-locality in continuous variable network using the spatial parity observables. So thank you.
Thank you so much, Sudeep, for the detailed presentation. So we may take one or two questions maybe. So floor is open for questions. Anybody?
I dropped question comment chat box.
Okay, how can this setup be extended to multi-party entanglement? Okay, I am not talking about loopholes here, but yeah, that can be done with JJ states. Yeah, that is already done. There is a paper by Chen. So Chen has proposed the concept of pseudo-spin measurements to observe non-locality, non-locality using two-mode squeezed vacuum. And after that, they proposed the same scheme for tripartite states as well. So you can see the paper. Okay, there are the next question about non-Gaussian state. There are many methods to create non-Gaussian states. We choose the photon subtraction because it is the most studied and it is easier to do in experiments. But yeah, you were talking about CAT states. Yeah, if you look at our paper, we have more examples. We have also included the CAT state as well. So we actually
Photon
talked about
counting as
entangled
well.
coherent state. Yeah. Can you repeat?
Photon counting, then we will create non-Gaussian state.
Photon counting, that is you are actually talking about different measurement.
Like CAT state, I don't have any idea about. That's why I asked question. I want to explain non-Gaussian state. Just
okay, actually, if you have a CV state, you can always plot a Wigner function of that state. Now, if the Wigner function is Gaussian, we call that state Gaussian, and if it is not Gaussian, that is non-Gaussian. That's simple. So,
Any other question? Thank you,
Hello.
Sudeep.
Yeah.
Okay. Satish.
Hello. Can I ask very small two questions?
Yeah.
So for first thing is whatever the network locality you are estimating can it be used as a metric of a network?
Metric, what do you mean by metric?
Metric means it's a performance of a network. I read a paper of Dr. Indranil. He calculated the average concurrence and used it
Metric
as a
is
metric.
some kind of measure which can quantify the quality.
Okay, actually, when you were talking about, you were always talking about some property. So if you were talking about non-locality, then obviously that will be a metric then.
Okay. And the second thing is, what do you mean by thermal noise in the network?
Thermal noise means there can be many sources of noise. So the model that I used, that specifically comes from the temperature of the atmosphere.
Okay. So it includes all the noises in the network, or it is some particular kind of noise due to the temperature only?
So it is a particular kind of noise. There can be other noises. So we consider this only. There can be white noise. There can be other sources as well.
Okay. Okay. Thank you.
I think it's time to move to our fourth speaker. Thank you, Sudeep. You may unshare your screen.
Okay, thank you.
So let us move to our fourth speaker, Javed Ahmed Malik from National Institute of Technology, Srinagar. His presentation title is Optimal Superdense Coding Through Noisy Channels by Escorting Qubits. So over to you, Javed.
Thank you, Dr. Priya. Am I audible?
Yes, you are audible, Javed.
Okay. Well, let me share my screen. Okay. So,
Make it full screen.
okay. Is it clear?
And if you are confident over your network, then switch on the
Yes.
camera as well.
Okay. So, am I audible and
No,
is the
you are
screen?
audible, your slides are
Yes.
visible, but if you are confident over your network, then you may switch on your camera also.
Actually, my network is not strong
Okay.
enough.
If you are not confident, please continue in this mode.
Okay. Thank you, sir. Thank you. So, well, myself, Javed Ahmed Malik from NIT Srinagar. I'm thankful to the organizers to allow me to present my work on one of the fundamental quantum information protocols, that's superdense coding. Okay, the goal of the work is to optimize this superdense coding under decoherence in presence of noise. This work is available on arXiv, and this is currently under review. So let me jump to the outline of the talk. I will be giving a brief motivation to address why the superdense coding is important. Then I will discuss the superdense coding protocol, and then I will discuss the proposed Escort qubit protocol, and then the results of our work. So let me first address this question, why this superdense coding is important. Well, superdense coding is a quantum information protocol. It actually enhances the classical information that can be sent over quantum channels beyond classical limits. So using this entangled resource state between two communicating nodes or two quantum nodes or two communicating partners, say else and Bob, else, for example, can send two classical bits by sending only one qubit to the receiver. Okay, so that is the superdense coding protocol. Well, it obviously has got these real life applications as well. It's useful in quantum networks and long distance communication. Now, being one of the fundamental quantum information protocols, and addressing these decoherence effects on this superdense coding becomes really important. Moreover, then proposing the protection strategies or mitigation strategies to decrease these noisy effects on the superdense coding becomes challenging and becomes important. So that's the task that we have taken in this work. Okay, let me begin with this ideal superdense coding. That's the superdense coding protocol. Now it involves these 4 steps, okay, which I have shown over here in this quantum circuit. It involves a preparation, preparation of the resource state, which is a Bell state over here. Okay. Now preparation is since preparation is local and it's controlled, so there is no noise during the preparation stage. Okay, and we as I have shown over here, there is a generation or preparation of a maximally entangled Bell state over here during the preparation stage. Now the noise kicks in during the second stage of the protocol, that's during the distribution of this entanglement. Now the two communicating partners, else and Bob, this entanglement is shared with these 2 qubits are shared with these respective partners. Okay, the first qubit, for example, shown with the subscript A, is sent to else, and the second one is sent to Bob. Now, during the entanglement distribution, during the transmission, the noise kicks in. So we need to address this this portion, and we need to apply the protection strategies at this entanglement distribution stage of the protocol. Okay, so over here I have shown ideal superdense coding. Ideal because during the entanglement distribution stage, in the ideal case, there is no noise acting on the system, and it is assumed that the shared resource state is actually a maximally entangled Bell state. Okay. So that is the second step. Now, once the entangled resource state is established between between the two communicating quantum nodes, that is between else and Bob, else encodes the classical information. Okay, and depending on the 2-bit string, whether she has to send 00 or 01 or 10 or 11 to Bob, she uses the unitary encoding, a Pauli operation, either identity operator or X gate or Z gate or a combination of the Z and X. Okay. Once the classical information is encoded, she then sends this encoded qubit to Bob. Bob then decodes the classical bits encoded by else. That's by performing a Bell state measurement on the 2 qubits, the already one part of the entanglement and the received part, received encoded state from Bob. Okay, that's the quantum superdense coding protocol, and the ideal quantum superdense coding protocol. Now, since there is no noise during the entanglement distribution process, Bob exactly obtains these 2 classical bits when else is only sending 1 quantum bit to Bob. Okay, that's the ideal superdense coding protocol. Now, now the noise acts during the entanglement distribution process, and these quantum systems being fragile, they are continuously interacting with the environment. Okay, and due to these interactions, there is decoherence and loss of quantum correlations, and the degree of entanglement is lost over the period of time. Now, to model these interactions, we use operator sum representation, where the evolution of a quantum system is given by these cross operators. Okay, and these cross operators satisfy this completeness condition to conserve the probability. Now, one of the most important environmental interaction or noise models is this amplitude damping channel. It's most prominent one, which is found in almost in most of the these physical quantum systems, whether in optical or photonic systems. For example, the loss of a photon, that's modeled by this amplitude damping channel. It actually models the spontaneous emission, that is the energy relaxation of a qubit from an excited state to a ground state. Okay, and it is modeled by these cross operators K0 and K1. Now, this cross operator K0, it actually corresponds to the no-flip trajectory of the amplitude damping channel. That is, if our qubit is in an excited state, it will stay in the excited state. This K0 tells you that it will stay in the excited state with the probability of 1 minus P. Or if it is in the ground state, then obviously it will there will be no decay out there. Now, K1 gives us the flip, that there is a decay from an excited state to the ground state with a probability of P. Okay, so this amplitude damping, due to amplitude damping, there will be both there will be a population decay as well as loss of coherence, and automatically the degree of entanglement, there will be a loss of this quantum correlations will be lost, and automatically the quality of our superdense coding, that will be degraded. Okay, since we are using our Bell state as the initial state during the preparation stage, the evolution of this Bell state during the entanglement distribution is given by this density operator, is given by this equation rho of t. Okay, where this KIA corresponds to the amplitude damping noise acting on Alice's qubit, and KJB is acting on the Bob's qubit. Okay. Now, in order to understand the effect of this amplitude damping channel on superdense coding, okay, we use the metric that's superdense coding capacity, and that's obtained by maximizing this Hollywood capacity over the encoded ensemble. Now, this encoded ensemble is generated by else. Okay, when she performs the Pauli unitary operators UK on her share of the entanglement. Since depending on the particular bit string, she applies either any one of those combinations of these Pauli gates, which I have already shown in the quantum circuit above. So she generates an ensemble. This Hollywood capacity, it actually gives us a maximum classical information that can be actually reliably transmitted over quantum systems. Okay, this capacity is optimized, or is maximized by taking equally probable these unitary encodings. Okay, in the ideal case, this superdense coding capacity becomes twice log of dA, where dA is the dimensionality of LS's subsystem, and for ideal case, it becomes two bits. That is, by sending only 1 qubit, 2 bits of classical information is achieved. So that will be the main quantifier or main metric that is used throughout this work. Well, here I have shown the effect of amplitude damping structure on capacity. Okay, I have plotted this capacity, superdense coding capacity, as a function of this gamma t, the dimensionless decoherence parameter, which quantifies the strength of this amplitude damping channel. Okay, and I have plotted the 3 noise configurations in our case. Since we are using a 2-qubit resource state, that's a Bell state, the noise can act on either LS's qubit or on Bob's qubit or on both the qubits. Okay, so we are considering all the possible noise configurations to see the effect of amplitude damping channel on the superdense coding capacity. As it's clear in all these figures, superdense this capacity, it decreases monotonically as we are increasing the decoherence strength. Okay, it's also visible in B in the Bob noisy case and both qubits under noise case. This superdense coding capacity falls below the classical limit. Okay, so that clearly shows how effective this amplitude damping noise is how drastically it actually degrades this entanglement and the superdense coding advantage as it takes the classical capacity below this classical limit of 1 bit. Okay, and automatically it necessitates the use of protection strategy to actually recover or optimize this lost quantum advantage. Okay, all right. So the main question that we have addressed in this work is we have actually restored this superdense coding advantage. Okay, look, there have been works regarding the suppression of noise and enhancing the quantum information protocols like weak measurement and its reversal or environment assisted measurement techniques. However, those techniques come up with certain limitations. For example, in environment assisted measurement techniques, we need to have direct access of the environment. We need to have control over the environmental degrees of freedom and to actually detect the quantum these fluctuations in the environment, to have track of the different possible quantum trajectories on the resource qubit. Okay, so but practically this environment having control over the environment is very hard. So our approach is to introduce escort qubits, the auxiliary qubits, okay, corresponding to every resource qubit that undergoes noise, that undergoes decoherence during the entanglement distribution stage. Okay, that's our approach to introduce auxiliary qubits. Okay, I will discuss in detail this escort qubit protocol. Okay, let me explain it from the this quantum circuit for better understanding. Okay, now look, this escort qubit superdense coding protocol is based on these 5 steps that I have shown in this quantum circuit. Okay, the first step again is the preparation of the resource qubits, which are this A and which are shown by this subscript A and B, as well as the preparation of these escort qubits, okay, which are shown by these subscripts EA and EB. Okay, so now these escort qubits are
Javed?
initialized in the excited state.
Javed, you
Yes,
have
ma'am.
4-5 minutes maybe.
Okay. Let me finish quickly. Okay. So the escort qubit is initialized in the excited state, and then this resource qubit is correlated with the escort qubit by a CNOT gate operation. Okay, then the resource qubit and its escort qubit, this pair is sent to each pair is sent to one pair is sent to else and another pair is sent to Bob. And during the entanglement distribution stage, they are sent through same quantum channel, okay, through the same amplitude damping noise channel, so as to keep track of all the possible trajectories. Now, this escort qubit, when it passes through the same noisy channel as the resource qubit, it is able to detect all the flip as well as no flip trajectories. And then there comes a third stage, that is the decoupling stage. Again, decoupling CNOT gate operation is applied between the resource state and the escort, and then this escort is post-selected, or it's measured in the computational basis state, and we are post-selecting the protocol based on its excited state of this escort qubit. When the escort qubit is observed to be in the excited state 1, it clearly implies that the resource qubit, okay, resource qubit the corresponding resource qubit corresponds to the no flip trajectory. That means it has not undergone any decay. So the protocol is then post selected on this no flip trajectory, and the resource qubit between the two communicating partners, else and Bob, is projected onto a maximally entangled Bell state. Now, with a maximally entangled Bell state as a resource between the between else and Bob, the usual encoding and decoding steps are employed, and the superdense coding of 2 bits is actually achieved. Okay, so this is the joint state of the resource qubits and the escort after the entanglement distribution stage, and accounting for all the possible trajectories. I will skip it. So this, after we have after decoupling CNOT gate operation and post selecting the escort qubits in the excited state, and that's by tracing out these escort qubits, we can see the resource, the state between else and Bob, the shared state between else and Bob is projected onto a maximally entangled Bell state, with the W being the success probability of this escort qubit protocol. Since we have neglected the other quantum trajectory, the protocol becomes a probabilistic one. And the superdense coding capacity, which is given by this equation CAD, in presence of escort qubits, is optimized to 2 classical bits. Okay, so in order to see the effectiveness of our escort qubit protocol, we have plotted the enhancement in the capacity and the corresponding success probability of the escort qubit protocol. So in the strong decoherence regime, as gamma t is closer to 1, we are seeing that the escort qubit protocol enhances the capacity. The maximum enhancement in the capacity is observed with a non-zero probability. Okay, so moreover, to account to see the effectiveness of our escort qubit protocol in all the possible noise configurations, whether else's qubit or Bob's qubit or both qubits are subjected to noise, we have performed a comparative analysis of the superdense coding capacity in the 3 cases. The dotted line over here, the black dotted line, shows the conditional capacity that we have obtained after the escort qubit protocol, and it is 2 bits for all the noise configurations, and it's independent of the noise strength of the protocol. Okay, the purple solid line, it actually is the average capacity of this escort qubit protocol when we are considering all the possible trajectories, both when we are considering both flip as well as no flip quantum trajectories for our superdense coding. Then we obtain this average capacity, and in all the cases, it is greater than this dashed line, that's the classical capacity, and the red solid line, that is the unprotected capacity. Okay, it outperforms the unprotected and the classical case. So this clearly indicates the effectiveness of our superdense coding, this Escort assisted superdense coding protocol. Okay, so to conclude, this Escort qubit protocol, it keeps a track of these noise trajectories and monitors the system environment interaction without actually having a direct control over the environmental degrees of freedom. And physically, this Escort qubit can be thought of as an auxiliary photon. For example, in case of photonic qubit for optical systems, going with the resource photon through the same optical fiber or through the same quantum channel. Okay, it can be so it becomes practically relevant. Obviously, we have optimized this superdense coding capacity to 2 classical bits by post-selecting and by post-selection of no flip trajectory. Now, since we have observed that there is no dependence, this Escort qubit protocol works for all the possible noise configurations, whether noise eject is on Alice's qubit, Bob's qubit, or both the qubits. Okay, it restores this superdense coding capacity equally for all the possible noise configurations. It automatically becomes a universal protection scheme which can be employed to any number of qubits, as well as for other quantum information protocols. For example, for quantum key distribution, entanglement-based quantum key distribution protocols to enhance this key rate, as well as for example, for quantum teleportation protocols to enhance the fidelity out there. So that is, I think, these are the main results that we have obtained in this work. So that's it. Thank you. If there are any questions.
Thank you for the excellent presentation, Javed. We may take 1 or 2 questions.
Yes, sir. I dropped my question in chat box.
So what is your questions? Okay, so there is a question. Phase damping with superdense coding.
Phase damping.
Okay, so in this in superdense coding protocol, it's strictly it will be strictly applicable to only amplitude damping noise, because it keeps track of these the decays from the excited state to the ground state. Okay, but strictly to phase damping, I won't be having a satisfactory answer to this question right now. I will look into it. Okay, so
I can
sorry.
in amplitude damping, we can face more errors. So we will prefer phase damping.
Indeed, we can. I think phase damping will be also modeled with the same, with similar these. I think the protocol will work better, I think, in phase damping.
Okay, thank you, sir. You have great pronunciation.
Thank you. Are there any
questions? I think there is no question. Thank you once again, Javed. You may unshare your screen. So now let us move to our last speaker of this session, Mr. A.R. Vatri Narayanan from UMDAE Center for Excellence in Basic Sciences, Mumbai. His presentation title is Quantum Hardware Using Spring. Over to you, Vatri.
And if you have few seconds at the end, then just tell us something about the center also.
Yeah. So first of all, is my screen and my
Exactly.
video visible?
Everything is fine. You
Yes,
are also visible.
yes.
Your screen is also visible.
Good.
Perfectly audible. So continue.
Thank you. Good evening. So I'm gonna present on quantum hardware using Springs. So my name is A.R. Badri Narayanan, and I am from UMDA Center for Excellence in Basic Sciences, Mumbai. So first of all, I would like to thank the organizers for giving me this wonderful opportunity to present my work. So I am just a master's student, so it won't be a very much of a work, but maybe you can understand it. So, into an introduction, qubits and quantum computing can be realized in a lot of ways. Example include ion trap quantum computing, NMR quantum computing, quantum computing, and using superconducting qubits, to name a few. So, this today's talk will focus more on superconducting qubits and a tool to analyze such systems. So, how do you build a superconducting circuit? So these are also called artificial atoms because you basically use a sort of like a chip to make like a tailor make a circuit which resembles an atom. So you basically cool a defined circuit to a material critical temperature into its superconducting phase. So these are a few examples of these circuits where the spring-like thing is the inductor, this thing is a capacitor, and this X means a Josephson junction, on which I will elaborate in some time. So the Hamiltonian of the second circuit, this circuit is given by H is equal to Q square by 2C plus phi square by 2L, where Q is the charge of the capacitor and phi is the flux of the inductor. And as you can see, this resembles very closely to the linear harmonic oscillator. So I can define appropriate creation and annihilation operators, and I can rewrite the equation to be h cross omega a dagger a plus half. So as I said, these energy levels mimic linear harmonic oscillator, but if you are working in quantum computing and if you are using qubits, this cannot be an ideal qubit system because all the energy levels are equally spaced, so it's difficult to control them. So how do we modify the energy level so that it just has two levels? So here is where Josephson junction enters. So Josephson junction essentially consists of two superconductors separated by an insulator. So once I add this system to the first circuit, if this is the energy level of the first circuit, the energy level of the second circuit with the Josephson junction becomes like this. As you can see, the energy levels are unequally spaced, and now it gives you more freedom to control qubits. Now that you have an idea of what superconducting circuits are, now we are going to analyze them. So the motivation behind that is superconducting circuits are like a very complex system which has a lot of Josephson junctions and a lot of these electromagnetic waves. So if you use traditional lumped element models or cavity QED derived techniques, it can also it can effectively become insufficient to capture these interactions. So hence I introduced to you this technique of energy participation ratio to effectively analyze qubits of higher complexities. So what is this energy participation ratio? It describes how much of this inductive energy is stored in a Josephson junction. To give a very rigorous definition, the EPR is the fraction of inductive energy allocated to a Josephson dipole when a mode M is excited. So this is the definition, and it can be a bit hard to understand this. So this is where the second part of the talk comes, using springs. So as you can see, this is a very common undergrad problem, which is basically a coupled harmonic oscillator. So this coupled harmonic oscillator has two masses and connected by springs K1 and K2, and they're coupled by Kc. So I can write the Lagrangian for this above system to be this equation 1, and I can rewrite this in a matrix form to be this, where these quantities define the matrix form. So these are the quantities. So now I rewrite the Lagrangian as follows. So basically what here I'm doing is I'm basically diagonalizing the Lagrangian. So here, as you can see, there's just I here, and this omega square is a diagonal matrix which consists of all the eigen modes of the system, the eigen frequencies of the system. So where this transformation consists of this q becomes like this q tilde becomes like v inverse q. So this is just I've just worked this out so as to show you how complex it becomes. So the matrix of interest here is this U matrix. So these are all worked out examples. So this is the eigenmode of the system, the coupled harmonic system. So the matrix of interest is this U matrix, which is the rotation matrix, which is given by this quantity. Now I define a new quantity called the participation ratio using this matrix terms of U, where the participation ratio is the square of this matrix. So I get the participation ratio matrix to be this, which is P1. So this is the participation ratio matrix. Now I can continue with my analysis. I can perform the Legendre transformation, obtain the Hamiltonian, which is given by this, where like this P takes the definition of canonical momentum, and this omega square gives you the eigen frequencies of the system. So this is the classical classical mechanics analog of a superconducting qubit in a 3D cavity, which I'm coming to now. So how do we implement this participation ratio in superconducting circuits? So so I take a superconducting circuit. So this is basically a transmon qubit, and this is a 3D cavity, a grounded 3D metal cavity, and this transmon is lying above a substrate, and this is grounded. So let's say this transmon has a capacitor of CQ. The equivalent capacitor of this transmon is CQ. The 3D cavities. So yeah. So this 3D cavities capacitance is CR, and it has also has in the inductance LR, and this transmon has a Josephson junction, so I can write this as EJ cos phi 2. This is the energy of the Josephson junction, and CC is the coupling, the capacitive coupling between the qubit and the cavity. So I can write the Lagrangian to be this. This is basically I have translated the superconducting circuit system to a classical mechanical problem, and I can now solve this using classical mechanics. So I write this again in the matrix form to be this is equation 17, where this LNL is a new term, which is the nonlinear contributions from the CJ cos phi 2. So I'm not going to go into the details of the solving here because I have already showed it before. So I can diagonalize this Lagrangian using this rotation matrix, which is given by these quantities, and I obtain EPR by squaring the elements of this matrix. So as you can see, like these, so there are few properties which is noticeable, but I'm coming to that later. So I obtain EPR like this very easily. So EPR is one quantity which is easy to obtain in like it can be difficult to do it by hand, but numerically it's very easy. So how do I obtain EPR? Like different is there any other way I can obtain EPR? So analytically, using elements of this rotation matrix, we can diagonalize the Lagrangian, and the elements of the square of the elements of the rotation matrix will give you the EPR. And but then you can do all like these systems analytically, right? So you need to use like numerical systems like COMSOL or ANSYS, IFSS, etc. So in that case, when you are designing the system, you can find EPR using these two formulae. So if you are just having one Josephson junction in your entire system, then this EPR is just given by this total electrical energy minus total magnetic energy divided by total electrical energy, which is just the fraction of things here. And if you are having multiple Josephson systems, then EPR is given by this half Lj Imj square by inductance. I will explain you now. So Lj is the linear inductance of the Josephson junction, the first order inductance of the Josephson junction. Imj is the total current flowing through the Josephson junction, and E inductor is the inductive energy in the whole system. So this E electrical, E magnetic, and E inductor, all these quantities can be found out numerically using finite element methods in COMSOL and ANSYS. So in finite element method, what happens is you take this cavity system and so the software breaks it down into say a few regions, and it solves the Maxwell's equation for each region. And then at the nodes, so it applies the continuity condition and it basically solves the Maxwell equation for the entire system. So that's how this is just a very beginner introduction to finite element methods. So this is how you find EPR numerically. So as you can see, there are a few properties which we can observe. So first of all, EPR is bounded. As you can see, it's just a fraction of some energy by total energy. So it should be between 0 and 1. The total EPR of a junction is conserved. So as you can see, it's evident here. If you add the sum of D plus A and you add this, if you can add this, you basically get 1. And if your total EPR of a mode is at most unity, so as you can see, if you add this column also, it becomes 1. And the vector EPRs of two dipoles are orthogonal. So I will define what vector EPRs are. So vector EPR is basically the EPR but with the sign of the rotation matrix. So this basically will give you negative. And as you can see, these two columns will be orthogonal. So this is the fourth property which we can observe. So these are the properties of energy participation ratio, and which makes, so how does it make things easy for us to analyze in superconducting circuits? So applications is that first thing is we can find the chi matrix. So chi matrix basically tells you the energy shift, energy level shift of the modes due to presence of due to the presence of various other modes present in the system. So there is something called self-talk and a crosstalk. So self-talk is the mode itself is making the energy level to shift. So that is also the unharmonicity. And the crosstalk is the energy level shift of mode due to the other modes of the system. For example, in this case, the qubit's energy level can shift based on the cavity as well. So cavity can also make the energy levels of this qubit to shift some some level. So so chi matrix gives you crucial information about the coupling between this qubit and cavity, and also between qubits and qubits if you're doing with multiple qubits. And so so as you can see, this chi matrix is very important. And alpha gives you the unharmonicity of a particular mode. So how this works is, so as you can see, we added a Josephson junction, and this Josephson junction can make it does introduce unharmonicity. So we need a measure to we need a measure of this unharmonicity. So this is given by this alpha. So how can we find that using EPR? So these are the two formulas. So this chi is given by this formula, where this omega is the eigen frequency of the system. This pi is the EPR matrix which I had defined here. And this EJ inverse is basically the matrix, diagonal matrix consisting of Josephson, the linear Josephson elements. So for this case, the first element will be 0 because the cavity does not have a Josephson junction, and the second element will be some number because the qubit does have Josephson junction. So EJ is that, and this is just transpose of the EPR matrix, and this is the eigen frequency. This is anyway diagonal, and the unharmonicity is just half of the the diagonal elements of the chi matrix. So using these quantities, we can study the qubit cavity coupling, qubit coupling, unharmonicity, and various other parameters efficiently. Various other parameters including decoherence times and all that. So having these tools will give you an idea of how the qubit performs. Like you can just design, run it in an FEM, see how the qubit improves, and we can run back and forth, and it helps easy in designing. So this is what I had. So with that, I would acknowledge Professor Vibhor Singh, who was my guide in IISc Bangalore. So Sudhir Ranjan Jain sir was also one of my guides. So Mr. Aman Tyagi helped me a lot in learning these techniques. And I would like to thank Professor Amarendra Kumar Sharma for introducing me to this topic. And finally, and last but not least, I would like to thank Yadanand for helping me with this presentation. So with that, I would thank you all. So I'm open for questions.
Thank you, Batri, for the nice presentation. Now the floor is open for questions.
It seems that people are tired, but some people are still joining. So if there is no more question, let's thank the speaker as well as the session chair, Dr. Priya Malpani, also the previous session chair, Dr. Guru Prasad Kadam, and let you all join me to thank all the speaker of day 2. It went well and almost in time. We're just 3-4 minutes late. So that's wonderful for when we are organizing so many talks. And so we'll thank you, everyone. We'll close now and we'll join again tomorrow at 6 p.m. Indian time. So thank you all.
Thank you, everyone.
Thank you.